Good morning, everyone. Today we have a special session of our internationalization meeting, which is directly related to the CAP Sprint project of UFPR. The workshop we have today is related to renewable fuels derived from chemical processes. The so-called internationalization program of UFPR is based on several, let's say, research areas. 5 of them are the main themes: biodiversity and environmental sciences, advanced materials, renewable energy and new forms of energy, bioscience and health science, and democracy, culture, and social development. We have many institutions worldwide linked to this program, but the number of missions, study missions or work missions that we had so far were reduced due to the effects of the pandemics. But even so, we have many activities involving several universities from North America and also from Europe. Today, we have gathered together an agenda to show a little bit of this work. We have people from these partner institutions, and the way I have organized the session is or follows the following rule of thumb. Let us put it this way. I would like to have one international speaking on behalf of the research involved in the project, and he or she will be followed by a presentation of a local UFPR staff who has been enrolled in a mission together with this university or eventually with another university belonging to the project. And today we start by inviting Dr. Fernando Lima from the West Virginia University. Dr. Fernando Lima joined the Faculty of Chemical Engineering of West Virginia University in 2013, where he is today an associate professor in chemical and biological engineering, and this since August 2019. Dr. Lima is also currently an adjunct faculty of the Department of Chemical Engineering of Carnegie Mellon University. And upon the completion of his PhD at Tufts University in 2007, he was a research associate at the University of Wisconsin and a postdoctoral associate at the University of Minnesota. He has received several research awards and is currently a member of the editorial board of the journal Process Control. Fernando, we are very happy to have you here, and I'd like to invite you to share your screen and begin your presentation.
Okay, can you see my screen now?
Yes, we do.
Excellent. Okay, let me get my pointer here. Thank you so much, Professor Luis Ramos, for the invitation, also for this opportunity to present today our project. I have a couple projects actually, and also the work that we're doing in conjunction with UFPR. So this is about some progress and opportunities that we will discuss on design, simulation, and control. So this is a process systems engineering presentation and the work that we've been carrying out here at West Virginia University. So Professor Luis Ramos already introduced myself, so I don't need to talk a lot about my bio here. But I just want to emphasize some of the research areas that we have been working on. As I said, this is related to process systems engineering. So we work with process design, process intensification, and then as well as advanced control, real-time optimization, and also optimization for design. We have also been working with machine learning. We'll talk a little bit about that as well today, including also some efforts from Industry 4.0, simulation, digital twins, state estimation, monitoring. Some applications that we have are membrane reactors, modular systems. And today I will be actually focusing on sustainability assessment, a tool that we have developed here with the US EPA. some pollution control, and also some approaches for decarbonization and hydrogen production in connection with the session here that we have today. So before I start the technical work, I'll always like to introduce West Virginia University, because many people don't know West Virginia and don't know where Morgantown is. So in case you're wondering, so West Virginia is here in the United States map. I think you're all familiar with the map, but not necessarily with the specific geography. But Pennsylvania is here, where we have Pittsburgh, Philadelphia, and then Washington, D.C. Below there. So it's actually quite close to many of these places. It's about an hour and a half driving to Pittsburgh, so that's very close, and then also about 3.5 hours to Washington, D.C. And it's very much in the north of the state here. As you can see, we have some photos here of our beautiful campus. This is part of the downtown campus. I know some of you, Professor Arias, who will talk later, has had the opportunity to visit. I invite you all, to come and visit us. So this is what we call a state university, public land grant research university. Is an R1, the highest grade in the United States, and currently has pretty much all majors, almost all majors, about 50 bachelor's, master's, doctoral, professional degrees, 14 colleges and school, and we have about 33,000 students. So it's a fairly large, middle-sized to large-size university in the United States. So let's go to the technical work then. So I'll talk about two projects. One is about sustainability assessment. The other one is about the Fischer-Tropsch work that we are doing. And the one I want to start describing here is the tool that we use, the GreenScope, which is a tool developed with the US Environmental Protection Agency. So let me talk about what this means. So we have the GreenScope tool here. That needs a lot of inputs. So it needs energy and mass balances, equipment utilities and costs, and also some properties of your system. For example, the regulatory list, some toxicology properties, some model parameters, and also defining like scenarios for sustainability, and as well as thermodynamic and physical chemical properties. So many of those are obtained from process simulators, or as well as from like CAS of databases of particular chemicals. So the input data that we need there, as I said, some mass and energy balances and some equipment data. And GreenScope actually translates this design and performance data into indicator scores in 4 categories: economics, efficiency, environmental, and energy. Here are the radar plots that you see. So the way we interpret those are that for each category, you have about 140 indicators total. So that's a lot, pretty much everything you can imagine. And for example, for efficiency here, the more broad or the more open the radar plot is, the more sustainable the system is. So you can analyze different scenarios, optimize it for sustainability. We also have economic indicators, environmental, and energy indicators. So you can assess technologies, novel technologies, renewable versus non-renewable, and then optimize for cost or sustainability. Of course, one of the challenges of this is the data availability, quality and quantity, because you need that to perform the sustainability assessment. And in particular, process simulators could be very helpful for that. So we work with ChemCAD, Aspen, Aviva, and others, other tools to obtain this data, because a lot of times you don't have necessarily experimental data to perform these studies. Of course, another limitation is that many of these software platforms don't have a lot of emission and pollution control capabilities in themselves. So we have to also work with pollution control units ourselves to model some of those and plug those into the process simulators to perform our assessment. So here is the tool that we developed. It's centralized around a user interface in connection with GreenScope. So imagine you start with a process simulator, could be ChemCAD, Aspen, or Aviva. They have streams, right? Those streams that you always see in the outlet, and you wonder what are we going to do with those, right? Those are the waste streams that you need to minimize. The air streams, liquid streams, and solid waste streams. We have developed pollution control unit models for those, for air, particulate matter, liquid, and solid. And those involve like thermal oxidizer, pyrolysis, paralyzer, the flare unit. There are a bunch of pollution controls there that we have available in the literature. And then along with the utility infrastructure, those produce what we call the life cycle inventory, not necessarily an LCA, but more of an LCI model. And those involve or include the report, input-output, life cycle, energy use, equipment sizing, utility consumption, as well as emissions. We have actually footprint as well. We do some design calculations to give you footprint of pollution control units so that you can analyze the trade-offs of implementing those units. So in the middle of this framework here, we have the interface that actually connects these pollution controls or LCI models with Green Scope, the one that I've talked about before, so that you can get your indicator results. So you can implement, for example, your sustainable solutions and then analyze those to see, did you get more sustainable? What happened to the cost? What happened to other indicators of Green Scope? And we have developed several different interfaces for this. For example, we have an Excel VBA. The Green Scope is currently in Excel, but we are converting that to Python as well in the future. But this has VBA can control the simulation actually and also connect those two interfaces there so that we can get pollution control and Green Scope assessment. So here's an example of this application. We actually have a recent book chapter that is coming out very soon with the NREL, the National Renewable Energy Lab. And this is an example of actually a bio feedstock here, the Opuntia. So we have done collaboration with University of Mexico, Hidalgo. And we have done several studies with Green Scope, but I'll present some of this today. But in this, we use a biomass feedstock here, this Opuntia, and that can produce biogas, biofertilizer, as well as pectin and mucilage. So this is an Aspen model that we have developed for that. And as you can see, you can produce the high value added fuels and chemicals based on this, and then you can assess the sustainability of this design. So I just have one snapshot. I know our time is limited today, so I have one snapshot of a result here of a radar plot where you can see we plot some indicators in the particular category here for energy, where we have energy consumption, energy intensity, energy recovery, energy for recycling. So we are currently optimizing this process. As you can see here, the energy and the actual environmental categories were pretty good. The costs may suffer a bit depending on what type of renewable source or feedstock you use. So you can then analyze the trade-off between the sustainability as well as the energy and cost aspects. We have also worked with process control for sustainability using this controller that we developed in-house, the BioCS, the Biologically Inspired Optimal Control strategy, which is an agent-based optimization approach. So this is centralized around this BioCS process controller. We have the set point that we feed to the controller, some constraints. And then based on the Green Scope, you can actually build dynamic radar plots. So I show you the steady state, right? For the Opuntia one, you can build a funnel with the dynamics for sustainability, analyzing that. And then based on sustainability parameters and some dynamic performance, you can actually optimize for sustainability. I will show you an example where we have like minimizing the water use, for example. So we can use this as constraints to define your control strategy. So as I said, we can generate dynamic 3D plots here depending on time. And then this can be done in a way that the controller can actually act online to improve the process sustainability of depending on your current operating points based on the indicators. So this is what I mean by this dynamic radar plots and these funnels. I have an example here of a fermentation process where we use this substrate to convert into ethanol in the presence of microorganisms. This is the traditional fermentation. We have some publications on that with conjunction with other collaborators from Puerto Rico, Mayagüez. And this is using the Zymo monomobilities, for example. We have a reactor here that we made into continuous with an ethanol selective membrane to produce and extract ethanol here. And the idea for this particular system is very challenging because it's non-linear. It has steady state multiplicity as well as oscillations for those who are familiar with this type of models. And those are everything I mentioned. We have citations here for you to access from literature. And in this particular case, we're interested in minimizing the water intensity indicator, this WI, so the water consumption. So we put a constraint of 70%. And as you can see here for this particular radar plot, this is the projection. We have always higher than 70%. And actually this radar plot opens as we go around with respect to time. So the funnel here that opens eventually starts within the lower indication here for water, but then it actually goes, as I said, remember, when it opens up, it improves the sustainability. So this actually shows that the sustainability index, SI, improves in terms of water intensity indicator as the time goes by. So for the second part of the talk here, the second project, this is the Fischer-Tropsch synthesis project. So in particular, this involves also our collaboration. I'll discuss this as well with UFPR. So the Fischer-Tropsch, as you know, use synthesis gas for the production of power and liquid fuels. And the synthesis gas can come from several sources: the reforming of natural gas, the gasification of coal, carbon capture, as well as some biomass source here, or biogas as well. We are using, for the current results, I'm presenting the natural gas, but we could also use biogas as well for this. And with the synthesis gas, you do the Fischer-Tropsch synthesis. You could go to several products here, as I said, power generation. You can have wax, right? And you can have liquid fuels as well here, connection with kerosene, naphtha, diesel. And it's important for that process to control your probability of chain growth. And you will see here, as that evolves, right? If you get a chain growth higher here, this changes your distribution of products, because there are so many products that you can obtain here. And I show you a couple of scenarios of what happens depending on what you have. So we have worked with a model, a slurry bubble column reactor model we took from traditional literature in terms of producing a high fidelity model, and then also reduced order model for our system studies so we can solve them quickly online. And these models use some cooling tubes for industrial Fischer-Tropsch for thermal management. Some of the variables that we have here, the manipulated variables, the coolant flow rate and gas velocity, the control variables, temperature, and the chain growth probability that I show you the importance of that. And here from the literature, we took this high fidelity model that they have developed, and then we produced actually a reduced order model for our studies. And I'll talk about the assumptions that we have for that particular model. So here's what it is. We started with a model based on hydrodynamics and thermodynamics derived from experiments. That high fidelity model has the large and small bubble holdup, the large and small bubble velocity, and the heat transfer. For our particular model that we use here, the simplified model that we came up with and validated, we use this large bubble portion here as a PFR. So we lump, it's more or less a lumped parameter model. For the small bubble part here, we have another well-mixed CSTR. And for the liquid slurry portion, we have this CSTR as well. We consider some phase equilibrium simplification, some quasi-steady state assumptions, as well as liquid phase for the reactor temperature. So the original model has 75 components, but then we simplified this, as I said, into 2 CSTR and 1 PFR equilibrium, so that we actually have some models that we can do here and work with it and solve it in a quickly manner online. And this is, we currently have a publication in preparation as well related to our efforts to this particular system. So what I want to show you today is about the machine learning efforts that we have for this process. So we're working with process operability, machine learning, and optimization of this reactor design. So we have used Gaussian processes for this, and in particular, nonlinear autoregressive GP models. So the GP NARX is one example. And for those who are not familiar with Gaussian processes, those are actually, you use these legs. So we have, for example, input legs, output legs to generate multi-step ahead predictions. So you can see here for this particular case, we have past output data, past input data, and then you obtain model predictions based on your JP NIRX models. So here is some sort of procedure, but this follows the typical machine learning approaches for model development. We use, in this case, our model that we developed to obtain simulated data. So we use pseudo-random continuous signals for generating the data. We discretize the model and run it at each time step. And then we employ the input-output data to generate the models and do the training stage of the machine learning. And then we assess the performance using cross-validation for the multi-step ahead prediction. And we analyze the mean, standard deviation, and the absolute error of these models. And then finally, we implement this models we can implement for steady state, but we are interested in doing the dynamic as well, the dynamic GP, which is also an area of contribution here from our group. So here are some of the results that we have for this particular system. So here's the chain growth probability, remember I described before, and the temperature. And the uncertainty bounds are shown here for you have the mean as the black line here and the system as well. And we have this grayish area here with the uncertainty produced by the Gaussian processes. As you can see that it describes pretty well the band around those two output variables after validation. And the nice thing about these Gaussian process models is that they are inherently provide you the uncertainty quantification for this. So you can see the errors and the error plots there. And then you can use this with the model-based and experimental-based data for gray box modeling, right? That's a hot topic. And future system studies. So some conclusion here, those are the two topics. I know there was a lot of material there, but I put here our QR code. Okay, you can point our phone if you like right now and I know this will be on YouTube as well, for you to access our group website, and you can see all our projects there. We currently have 12 PhD students, about 20 people in the group, so there's a lot going on. There I have my email here as well. I would like to acknowledge our project here. I know some of our collaborators are here, Professor Luis Ramos, Coraza, as well as Professor Eiras, who will talk later. Would like to acknowledge the funding source. We have the WVU UFPR Araucaria Foundation partnership, the NAPI HCR project on the development of technologies for shale gas and biogas conversion to value-added fuels and chemicals in West Virginia and Paraná. So there's a two-state collaboration here from different countries. The future directions, I've been talking also actually to Coraza and the team to bring students here, and also professors, as I said, everyone is invited to visit us. We have talked to Maringá, UFPR, UniOeste. One student from UniOeste is already planning the visit, okay, for the next couple months. And in the future, we will work on the dynamic modeling and optimization for the Fischer-Tropsch with biogas in collaboration with these visits and as well as others at UFPR. And with Professor Eiras, who will talk next, we're discussing the modeling and optimization of membrane processes for CO2 capture. So with that, I will pass it to Professor Eiras, Daniel Eiras, to discuss that, and Professor Luis Ramos, back to you as well. Thank you again, and I'll be glad to take any questions later on.
Thank you very much, Fernando, for a very impressive talk. Very interested in the tools that you have developed for sustainability and how could that fit into the projects that we are involved with here in Brazil. And the collaboration with you will most certainly contribute a lot. So I'm looking forward to the results that are coming from this. I have planned to take questions at the end, though questions here in this environment are difficult to handle, but we'll see how it goes. Let us hear Daniel next, and then at the end of his talk, then we might eventually come to some discussion about the things you have shown us.
Thank you.
So with this, again, I thank you, and we move on to Professor Daniel Eiras. He's an assistant professor at the Federal University of Paraná and head of the graduate program in material science and engineering at the same university. He has a bachelor degree in chemical engineering and a master degree and PhD degree in material science and engineering, with an international experience at Georgia Tech, working with composites and nanocomposites. After his PhD, Dr. Eiras worked for 2 years at the Federal University of São Carlos in Brazil in a project that was sponsored by Technip to produce polymer nanocomposites for flexible fuel tubes, and this applied to oil and gas production. Currently, his research is focused on the modification of polymeric materials to produce blends and mixed matrix membranes for gas separation and water treatment. So Daniel, thank you very much for taking our invitation, and the screen is yours for your 15 to 20 minutes talk.
Luis, can you see the presentation?
Yes, all good.
Okay. Thank you, Luis, for the opportunity to participate on this these presentations from CapSprint. I had the opportunity to meet Professor Fernando and his group at West Virginia University. And I have to say, both the university and the city, Morgantown, are very, very nice place to go. I was well received there, and I really enjoyed my time with Dr. Lima, Dr. Sanial, and all the research group. So I just want to take the opportunity to thank Professor Lehman and his group for the reception that I had there. Now, what I'm going to talk about is the application of polymer membranes for gas separation, basically. Okay? So I will present some fundamentals of gas separation and how that relates to material science, and try to show some examples of what we're doing here at the Federal University of Paraná. So the transport of gases through polymer membranes can take place by two mechanisms. One is facilitated transport that I'm not going to discuss here, and the most common one is called solution diffusion. So based on solution diffusion model, the permeability, that's P here in my presentation, is equal to the product of the diffusion coefficient and the solubility coefficient. So if we want to improve polymer membranes, we have to deal with the diffusion coefficient and the solubility coefficient. The diffusion of gas molecules in membranes, in polymer membranes, is basically explained with the diffusion jump. So usually the gas molecule is absorbed by the polymer. Then a transient space or a transient hole is created inside the polymer membranes by the movement of the polymer chain. This creates the space necessary for the gas molecule to jump from one sorption site to the other sorption site, and after that, this space collapses and another space opens, so diffusion can continue. This mechanism depends a lot on the flexibility of the polymer chain and the fraction-free volume. That are two aspects that we try to control when we modify polymer materials. The sorption, that basically means absorption and adsorption. The sorption in polymer membranes is explained by what we call the dual mode sorption mode, which means there are two populations of spaces where you can sorb a gas molecule in a polymer material. One is modeled by the Henry per meter, that is the Kp, and the other is the Langmuir. So Henry basically is absorption, and Langmuir would be adsorption. So the gas molecule is strong, absorbed by the Langmuir spaces, and the interaction is a little weaker for the Henry spaces. So this is basically how we model or we explain the permeation of gases in polymer membranes. So what happens when we modify the polymer membrane is that we change either the diffusion coefficient or the sorption coefficient, or both, depending on the situation. One way to understand that is to analyze the relationship between the selectivity, that it's the alpha parameter here in this first equation, and the permeability, that is the PA in the same equation. So there is a direct relationship between the selectivity and the permeability that we call the trade-off. So there is a compromise between these two properties, in which when we increase the permeability, we decrease the selectivity. If we increase the selectivity, we're going to decrease the permeability. And that's very unfortunate because what we want is to increase both at the same time. Okay. Analyzing this first equation can be modified to correlate the selectivity, the diffusion coefficient, and the solubility coefficient, dA and SASB. So based on that equation, what we can do is that what we can get from that equation is that if we increase the diffusion coefficient, we're going to reduce the selectivity. So we increase the diffusion coefficient, we increase the permeability, and we reduce the selectivity. At the same time, we can increase the solubility selectivity as A divided by SB to increase the selectivity. So the two ways that we can improve the properties of polymer membranes is to modify the polymer, so we change the diffusion coefficient, or we change the solubility selectivity. The problem we usually have is that when we increase one side, we end up decreasing the other side. So we increase permeability, we decrease selectivity. For example, we can increase this parameter SA divided by SB by introducing specific chemical groups, like ether groups, inside the chemical structure of the membrane. When you do that, we're supposed to increase the selectivity. At the same time, this group increases the flexibility of the membrane and increases the diffusion coefficient, which is going to reduce the selectivity. So bottom line, what we do is that we try to modify the polymer membrane and deal with this trade-off that is common for polymer membranes. As you can see in this figure, that relates the selectivity of CO2 and methane with the permeability of CO2, is that some polymers, some new materials can surpass the limits of the trade-off and the upper bound. So the points in blue are polymers like TR polymers, thermally rearranged polymers, high-tech materials that can surpass these limits of the upper bound and kind of cheat on the trade-off problem. Okay. So what this figure shows is that because of the trade-off, we have an upper bound, okay, a limit for the properties of polymer membranes. Okay, so we have the prior upper bound that was developed in 1991, and the present upper bound that was developed in 2008 after the development of new materials. And then we have very specific materials that are the blue points that can surpass these limitations of polymer membranes. So to show what we do here, this is the work of one of my students, Arthur. He modeled membrane separation process to see how the application of different materials would influence the process. So we have here 4 different materials. UPB stands for upper bound. So he took the equation that I showed in the last slide and plugged that in the model. And then we have polysulfone, that is PSF, that is a commercial polymer, usually used to produce membranes. And then we have 2 high technology materials. TR450, that is a thermally rearranged polymer, and CMS, that is a carbon molecular sieve membrane. What you see is that when you change the material from upper bound to CMS, is that we reduce the cost, the overall cost of the project, the process, and we strongly reduce the required membrane area for separation. This is for biogas. We are thinking about biogas here. So what we do when we change materials is that we reduce the total area and the size of the equipment that we need to produce some separation. Okay, so that's one of the reasons that we use that we study new materials for membrane gas separation. to try to reduce the size of the equipment, to try to reduce the cost of the separation. Based on that idea, what I do, what I've been doing in my groups, is to develop what we call mixed matrix membranes. Mixed matrix membranes are materials that are formed by two different types of materials. I can use a polymer and a zeolite. I can use a polymer and a polymer with a different structure to form mixed matrix membranes. So one of the works I've been doing is with this material called PBAX, that is a copolymer that combines a polyamide group, PA group, and a PEO group. So the advantage of this material is that the PEO group has great interaction with CO2. So it basically increases the term SA/SB in the equation of the selectivity. So this material has a very high selectivity for CO2 over methane and CO2 over nitrogen. So it can be applied for biogas or natural gas separation and carbon capture. Another interesting fact about PBACs and copolymers is that they can form different morphologies depending on how you process them. So I've been working with this material and trying to modify him with different approaches. One of which was to use polydopamine, which is a natural material, a natural polymer that was first synthesized, inspired by the ability of muscles to stick to different surfaces, even in harsh environments. The synthesis of polydopamine is very simple. You can make by oxidation of dopamine hydrochloride in alkaline conditions, pH greater than 8. And polydopamine is mostly used or applied to modify surfaces. Okay. So here's this picture is a representation of polydopamine that was synthesized here in my group in our laboratories. We see here that the size of polydopamine changes when you change the conditions of the synthesis. Bottom line, what we're doing here is to reduce the amount of ethanol that we use in the mixture of water ethanol that is the medium for the synthesis of polydopamine. One of the possibilities. So the structure of polydopamine, it has indole groups covalent linked with some amine groups, and these particular groups have strong interactions with CO2. That's the reason why I have decided to use polydopamine. It is also interesting that polydopamine has a stacking or a stacked structure that has a distance between the molecules of 0.34 nanometers that coincides with the size of many gas molecules like CO2, methane, and nitrogen that we want to separate. So, based on that chemical structure and this stacking structure, I thought that polydopamine could improve gas separation properties of PBACs. So here's some of the evidence that we have. Polydopamine may have some melanin in its structure too. And as you can see here, the interaction of both melanin and indole groups of polydopamine is very strong with CO2. This is modeling. This is a reference that I found. So what I expect from this work was to increase the permeability and increase the selectivity by changing the parameter S, okay, the solubility coefficient, and also increase the selectivity due to solubility, which is the term SCO2/S nitrogen. Okay. With that, I could, at least in theory, increase both selectivity and permeability. So I would not reduce the permeability. I would skip the trade-off problem. So there has been some previous publications about the use of polydopamine for CO2 separation. They basically synthesized the polydopamine and added it to the polymer, incorporated into the polymer. So what we did, instead of doing what we call ex situ polymerization is we did in situ polymerization. So we combined the dopamine hydrochloride with sodium hydroxide and mixed that with the P-bags in a solution. After 24 hours, we believe we have the polymerization of polydopamine inside the P-bags membrane. So instead of doing 2 steps, we did only 1 step, and after that, we already had the polymer membrane ready to test. So what in situ polymerization does is that it reduces the interactions between the polydopamine molecules. It also reduces changes the kinetics of the synthesis, the polymerization, and it has been used in projects to produce fluorescent particles in a process called conjugation. So what we expect with that is that we're going to put those stacked molecules apart, and they could interact with the polymer. Not only the polymer, but the gas, especially CO2. The results we get are in this table. As you can see, the permeability of CO2 is reduced with the incorporation of polydopamine. So this is the concentration of dopamine hydrochloride that we have here. We are increasing the concentration, and what happens is that the permeability is reduced. At the same time, the selectivity is increased. So basically what we did is that we got part of our work done. We get to increase the selectivity, but we reduced the permeability, which is unfortunate, but okay, it happens. So if you increase the selectivity, but we decrease the permeability, okay, what problem happened is that the diffusion coefficient was reduced. Okay? So we are mostly sure that this term S is increased with the incorporation of polydopamine. We have information from the literature that the term S has increased. So in order for the permeability to be reduced, the term D has to be decreased. To explain that, we could do only simple sorption tests, but we don't have that kind of equipment here yet at our lab. So we have to explain that in different ways. If the diffusion coefficient is being reduced, what's probably happening is that polydopamine is interacting somehow with the polymer, reducing the flexibility of the polymer chains, or reducing fraction of free volume. So those are the 2 mechanisms that can reduce diffusion coefficient. So based on DSC results, colorimetric results, we can see that the melting points of PEO, of the PEO blocks, are increasing, while the melting points of the PA groups are reducing. The increasing in the melting points of PEO show that there are stronger interactions between these groups, which means that the flexibility or the mobility of the polymer chain is being reduced. So that explains part of the result of the decrease in the permeability. At the same time, the decrease in the melting point of polyamides, the PA group, indicates that polydopamine might be between the polymer chains, reducing the interactions between, but at the same time reducing fraction free volume. I'm using these results just to illustrate the kind of work that we do here. When you modify the polymer, there are certain interactions that are difficult to expect, and that influence the polymer. So we were expecting just to increase the solubility selectivity, but we end up increasing the diffusion selectivity by reducing the diffusion coefficient. That resulted in a decrease of the permeability. So what we basically do in our group is to modify the material and try to understand what happens when you do that kind of modification. Usually, when you do composite materials, we end up with problems like that. The interaction of the different phases that form the material end up influencing the properties of the membranes and giving us results that are different than expected. Okay. Again, we managed to increase the selectivity, but we did that by a decrease in permeability. So we did like half the work we wanted to do. The last work I'm going to show some results is that we are modifying polysulfone with lignin particles to create mixed matrix membranes. So I show here two pictures of lignin particles. These are actually lignin iron particles. The concept here, it was supposed to be pretty much the same of the previous work to increase the selectivity of the solubility selectivity. And what we did is that we synthesized these particles by co-precipitation using different solvents. So the spherical particles are produced by a mix of THF and water, and the other one is produced by a mixture of DMF and water. Okay. So you can see clearly that we can get spherical particles with THF, but we cannot get something very spherical with DMF. This has to do with the solubility of lignin in those solvents. So here's that one was an SEM result. Here I have a TEM result that confirms that the THF particles that are spherical, while the DMF particles have some elongated morphology, a different morphology than expected. So when you incorporate only lignin, okay, in the polymer membrane, what we have is a huge increase in permeability compared to the pure polymer. Here is the CO2 permeability is supposed to be around 5 or 6 bar, but we don't have a lot of selectivity. Okay. Some of the results here show some selectivity, but in most of the case, what we have is a selectivity close to 1. Okay. That means basically no selectivity. The same thing happens when you incorporate the lignin iron nanoparticles. Okay. We have huge increases in permeability and no selectivity. For some of the results, okay, the first table was DMF nanoparticles, here are THF nanoparticles. For some of the results, we end up seeing some selectivity, okay, with increases in permeability. So the reason why I'm showing the results like that is that we have a lot of variation. We didn't have a very specific trait in our results. So we represent the data like that. So some of the samples have better selectivity. Some have a worse selectivity or no selectivity. To try to understand what's going on, we did many tests and we end up with the SEM results of our nanocomposites. As you can see here, we have a particle that is inside the polymer, and there's a huge defect around the particle. So what we believe happened here is that although we had the nanoparticles incorporated in the polymer, those nanoparticles were not compatible with the polymer. There was a problem of interaction. So what happens here is that the gas, instead of passing through the polymer or through the particle, they're going to come around and simply pass around the particle. That explains why we don't have selectivity in many of our membranes. Those defects are very difficult to control. It's very difficult to avoid those defects. And what happens is that some membranes have defects, other membranes don't have defects. Those that don't have defects, they end up having a good selectivity, although a smaller permeability. Those membranes that have defects end up having a very small or no selectivity at all. So my goal here with this presentation was to show what we do and how do we do these material science concepts to produce and understand the behavior of polymer membranes. There are many details that I didn't tell here because of the time, but if anyone has questions about the work we've been doing, I'm glad to answer. So, membrane separation technology basically depends on material science engineering. What we've been doing here, we are dedicated to combine different types of materials to create solutions that will improve gas separation membranes. At the same time, my group's dedicated to understand how these new materials behave by studying different properties. So we don't characterize only permeability and selectivity, we do the thermal properties, mechanical properties, other characterizations. And the final goal is so we can establish the correlations between the structure, processing, and properties of polymer membranes in mixed matrix membranes. Thank you for your time. Thank you, Liz, for the opportunity to be here. And if anyone has questions, I'm happy to answer.
Thank you very much, Daniel, for a very nice presentation. Of course, we couldn't hope for a better start. Two very interesting talks, but the problem is we are a bit over time, so I cannot open up the floor for questions. Fernando, I have sent you a message in our chat. If you have to leave, please do so due to your other commitments for the morning. So thank you very much again for being with us. And of course, if you can extend your stay for a bit longer, you're welcome to do so.
Thank you.
So with this, we move on to our next block of presentations, two presentations in sequence. We are very fortunate to have Dr. Juan Ordonez with us today. He is at the FAMU FSU College of Engineering since 2003, where he is now a professor of chemical engineering. His research lies within heat transfer and applied thermodynamics and their application to design, modeling, optimization of advanced energy systems. Specific research areas include renewable energy systems, solar thermal systems, modeling and optimization of heat exchangers, fuel cells and fuel cell systems, HTS motors and cables, combined heat and power, and photobioreactors for microbial growth. He's a member of the ASME and Sigma XI networks, and he has served as associate technical editor for thermal engineering since 2005. So with this, I welcome Dr. Juan Ordonez for our workshop, and please try to be within time because we are already a bit late in our session.
Thank you very much. Can you see my screen? I'll put a PowerPoint here. Can you see it?
Yes, we do, Juan. Thank you very much.
All right. So thank you very much for the invitation. And I enjoy very much the meetings I've seen so far.
Juan, can you turn your camera on so that we could see you?
Let me see.
Yes.
Yep. Now.
There you go. Thank you. Welcome in.
Thank you. I want to talk to you a little bit about a framework that we are developing to evaluate the role of fossil energy, primarily fossil fuels, really, into the hydrogen economy. It connects well with what Professor Lima showed, so I would like to talk to him later about opportunities. We are located in Tallahassee, Florida. It's in the Gulf of Mexico, and there is a site called Innovation Park, where we have multiple laboratories. Particularly, I work at one that's called the Center for Advanced Power Systems. It's mostly electrical machines, modeling, hardware in the loop simulations. But we have efforts on thermal management and renewable energy that I will discuss. We also have a smaller center called the Energy and Sustainability Center that has places to test concepts around hydrogen, photovoltaic systems, in integration to residential settings. So, going to the topic of what I want to share today, I'll talk a little bit about the motivation and background for the use of hydrogen. I'm assuming all of you are familiar with the tremendous growth in investment in hydrogen research and what we are trying to do. So our objective is to tackle or to create a framework to evaluate and guide the decision-making process on the role that fossil fuels can play in addition to renewable sources of hydrogen within the hydrogen economy. And here I show a complicated diagram with many things, but you recognize that there are sources of where we take the electricity that will be needed in the production of hydrogen, different sources, in this case methane, gasification, and methods that are associated with this production, the carbon capture, the storage, and the electrolysis as a baseline for comparison. There is, when developing an infrastructure for a country or for more than that, for a continent possibly, there is considerations regarding the gas infrastructure, the use of the ports, and many other infrastructure that are not obviously connected to the production itself of the hydrogen. There are many uses of hydrogen that are envisioned. Some are already, the reason we use hydrogen today are essentially the production of fertilizers, the refining of materials, and some upgrading of fuels. But as you know, there is interest in using hydrogen for transportation, for residential applications, and possibly many more. So our goal is to establish tools to evaluate something that connected to the previous talk on environmental or sustainability assessment. So we're trying really to do metrics for CO2, global warming potential, energy use, and water use. The production of hydrogen, as you're familiar, there are many methods. One is from metals. So this is one of the first methods to produce hydrogen was from iron. There are also several aluminum reactions that produce hydrogen. And actually, Professor Vargas is studying some of them. And the most commonly or widely used are from fossil fuels through partial oxidation, through steam connections. And this CO that is here is further processed to hydrogen through the Schiff reaction. There is also other methods. The thermal decomposition is used from alcohols. And of course, we have water electrolysis. And there are biological methods. In particular, for our groups, we are interested in microalgae use. Today, about more than 90% of the hydrogen that is produced today comes from fossil fuels and is produced not using renewable energies. There is a classification that started with 2 or 3 colors. Now it's a whole lot of colors on associated to hydrogen. So people talk about blue hydrogen, gray hydrogen, green hydrogen, and many more, depending on the source really that we are taking. So the most commonly used spoken today are the green hydrogen from renewable electricity through electrolysis. But today I will talk a little bit about gray hydrogen that is using fossil fuels through steam methane reforming or gasification, and as well as the blue hydrogen, which includes the carbon capture from at different stages of the process. What I wanted to point here is that a very, very small fraction of the hydrogen that we use today comes from renewables. A lot of it from natural gas and a lot of it from coal and other fossil elements. What is interesting in hydrogen? I think I mentioned a few things, but it's not a new story. It's been used for air transport since the 1783 for air balloons, and now there are more modern concepts in transportation, and particularly interest in aviation. So that's why I'm putting this picture here, but there are many, many more examples. This is one question that I'm calling a big picture question, is the following. What role should, if any, the fossil fuels play in the development of this envisioned hydrogen economy? And one question associated to that is can the fossil energy complement the introduction of renewable forms of hydrogen production? So a little bit about the hydrogen use in the United States. Today, the United States uses about 10 megatons of hydrogen per year. And the question I pose here is, could we generate it today from electrolysis using renewable energy? So could we supply the United States needs for hydrogen today using only renewable and only electrolysis? The very simple calculation that I made is described here. So these 10 megatons are these 10 billion kilograms. And if you take an ideal electrolyzer, you will need 141 megajoules per kilogram. In other words, it tells you that to produce those 10 billion kilograms, you will need about close to 400 billion of kilowatt hour of energy. The United States electricity generation in 2020 as a whole was 440 billion kilowatt hour, and 17% of it came from renewables, so about 693 billion kilowatt hour came from renewables. In other words, to close the story here, if you were to use renewable energy to produce hydrogen through electrolysis, you essentially will have to use all the generation today. Of course, we are hoping that this changes, that this green pie becomes much bigger, and there are a lot of investments to make so happen. So the answer is that today is not possible, but hopefully the situation will change. The needs for hydrogen in the United States are estimated to grow from 10 to about 85 megatons per year. And here I show you very briefly the different sectors. So how are we approaching this? We are taking this structure borrowed from some studies in the UK that we're calling a supply chain superstructure. And essentially, there are columns and rows. The columns are steps in the hydrogen economy chain. So we have production, storage, distribution, transmission, and at the end the use. And rows are different options. Here I put some that you recognize: steam methane reforming with and without carbon sequestration, coal gasification, biomass gasification, autothermal reforming, water electrolysis, and multiple ways of store, transport, and at the end use. The approach what we're trying to do, I'm repeating the story, but telling you again what we were trying to do is to try to quantify for subsets. So if you were to pick routes here, how much fuel is used, how much energy is used, how much water is used, establish a levelized cost of hydrogen and a life cycle analysis cost. So with this in mind, we started quantifying water use. I'll talk to you about a little bit of water use quantification and the CO2 emissions quantifications. The initial stages of our work were on quantifying the explicit water use, and I'll show you a little bit what I mean by that. This is a graph showing the use of energy per kilogram of hydrogen produced as a function of the electrolyzer efficiency. With this in mind, you can now estimate how much water is needed for water electrolysis. So the center graph shows you my estimates, and we're done in the following way. In the x-axis is the electrolyzer efficiency, and you see three lines. The lower line is the water that is used directly to produce this kilogram of hydrogen, meaning the one that is going to go into the electrolyzer. But the electrolyzer is powered by electricity, and electricity, there is a lot of water consumption in the generation of electricity. The numbers that generated the orange and the green lines come from the average generation in the United States. So the average generation in the United States tends to be close to a thermoelectric power plant. The thermoelectric power plant has a cooling tower, and the cooling tower uses water for cooling. Sorry, I'm getting here phone calls and things. The use of water in the cooling tower is of two ways. One is consumed actually in the cooling, and other portion is just withdrawal. So it's taken, but is somehow returned. So now, what the message here is that there is a very significant consumption of water in electrolyzing water, not only because you need water, but also because you need electricity. We're comparing that to other methods, in this case to the methane reformation. And we have here the standard methane reforming followed by the shift reaction. And the idea is that from a water perspective, it's not completely clear that the electrolysis will be more beneficial. One thing that we did is a second step was to look at the disaggregation of this average. So these numbers that I show you is an average. It's a very diffuse in a sense that we are just looking at one value for the water need to generate a kilowatt hour. What if you try to look deeper? So we look at many forms of electricity generation. What if it comes from renewables, or if it comes from nuclear, natural gas, or coal? And it again is mostly connected to the type of cooling that your power plant has. The most common cooling systems are these illustrated here, the ones through the tower and the dry cooling. And because you have many alternatives of generation and multiple cooling generations, you end up with a very long list of options. Here you see that a few at least of those list of options. Photovoltaic, wind, concentrated solar power, and many more. And as you see, they are divided on the cooling type. And even within a given cooling type, there are other subdivisions. What I'm trying to, or the takeaway here is there are many options of generating this electricity and many options within or sub-options that for the cooling. And that will impact the water use in your whatever it is that you do with this electricity. In this case, we are looking at the production of hydrogen. With that information, we were able to then map it to this other plot that you've seen before, and look at the impact of the type of generation of your electricity and the type of cooling ultimately on the water consumed in the generation of hydrogen per kilogram of hydrogen and the electrolyzer efficiency. So we have done this for every element in that table. I will only show a couple of examples. This is a biopower, and here there is a concentrated solar power and a few technologies. You see that depending on your cooling, again, these are dry cooling, so you very little water use. These are other types of towers. This is a central tower receiver that probably has it certainly has not a dry cooling, it has a water cooling system in the power block. Then the water consumption increases. Other aspect of our effort was the simulation or the estimates of the emissions. And we are trying to do it not for a single, at the end, I won't get there today. The idea is to do subsets along the route from production to use. So I will talk a little bit about the methane reforming with and without carbon capture and sequestration, and in particular about the emissions and how are we computing them. there is a very interesting paper by Howard and Jacobson on trying to answer this question: how green is the blue hydrogen? It goes back to the colors that I was telling you about. And they do a very detailed guidance to the estimation of the CO2 equivalent emissions in the process of production of gray hydrogen from methane. And essentially, you're using natural gas, essentially methane, to the steam methane reforming reaction, which requires some heat, and you produce hydrogen. There is a lot of places where you see CO2 emissions and potential methane emissions. Their estimates are founded on three particular parameters. One is the leakage of methane. So you see the quotes here. The other is the indirect upstream emissions that are, again, the CH4 that can leak here, and the use of energy that is required per cubic meter of hydrogen that is produced. So there are certain parameters that have uncertainties. They document them very well, but are still kind of the key to the results. So we did a study on the uncertainty of those parameters. We did that by generating Sobol samples around Gaussians, essentially around the base estimate for each of these three parameters, and did later on tracking of the global warming potential that results from the emissions of this fugitive CH4 and CO2 that is emitted in the different stages. And with that, we were able to reproduce their work, but now with these uncertainty sliders, if you wish, on the three parameters, that leads to now a probability of the emissions being within a certain range. So we have now some uncertainty quantification behind the study. There is a sensitivity approach to this, so we are able to look at the influence of the three parameters that I mentioned, and in particularly our study suggests that the CH4 leakage is the key. So if you assume that there is no leakage, you'll get a completely different story. If you account for leakages, you will have a very different conclusion. We've done it for many other considerations or structures, so including carbon capture sequestration at different stages. I will not repeat that. And I'm 40 more seconds. So the idea, or what we are getting to, is we are trying to generate what we call in a dashboard, essentially a tool that you can interact with, and you can place yourself in a map. This will trigger information that is local, like electricity cost and so on. You have sliders for some of the parameters that I mentioned, the fuel cost, the capacity factor. It produces dynamically, so as you change these numbers, it dynamically changes this levelized cost of hydrogen, and for different technologies, in this case, steam methane reforming, autothermal reforming, and some others, as well as information on the emissions. And I think that's it for my 20 minutes. So thank you very much.
Thank you very much, Dr. Ordones, for a very interesting talk, touching very relevant issues about the hydrogen economy. This question about the fugitive methane has become an issue, especially after the events at the Russian-Ukraine war. And yes, I mean, it's very important to understand how green is blue, or how green could blue be. Let us put it that way. But I do agree with you that we have a long way to go to be able to supply green nitrogen to the needs of our society, being US or wherever else. So yeah, we do have a long way to go. But let us hear our next speaker, and if we do have time at the end, maybe we will open the floor for a couple of questions. So our next speaker is Dr. Jose Viriato Coelho Vargas. He's a full professor at the Department of Chemical Engineering at Federal University of Paraná. He obtained his PhD from Duke University in Mechanical Engineering. He leads the Energy and Thermal Science Group at UFPR and develops theoretical, numerical, and experimental scientific research in alternative energy sources, oil refining processes, cogeneration and power systems, heat and transfer, heat and mass transfer, biotechnology, and biomedical engineering. As I said, he's the head of the Sustainable Engineering Research and Development Center in Brazil, at UFPR Brazil, where microalgae is exploited as a source of biodiesel and other energy carriers and other products. We're very happy to have you here, Jose, my good friend. The floor is yours. Please make it use of your 15 to 20 minutes, but the shortest, the better.
Good morning, everybody, and thank you, Luis, for the invitation. And I hope I can comply with the 10. I hope to speak only 10 minutes. And my talk today, can you see? First, let me ask: can you guys see my screen and myself?
No, we see you, but we don't see your screen yet.
Really? So I share the screen with the JIT.
I hope you are not having the same trouble I had in the beginning of the session, because
Really?
I haven't been able to share my screen from the very beginning.
Let's see. Okay, full screen. Okay. Okay. Let's see it now. Can you see my screen?
We share screen, but we don't see your
Presentation. Okay.
your presentation yet.
Now you can see it, right?
Oh boy, not yet.
Can you see it?
Nope.
Nope. One is here to help me. Okay. I'm not familiar with this.
We do
with
see
this
your
JIT
screen
tool.
because we do see your screen, but we don't see the PowerPoint projection.
Can you see now? No?
No, not yet.
Okay. Let's do it again. Okay. Go here.
I can see it is.
Yeah, now we click here. Yeah, now you will see. That's for sure. Can you see now?
There you go.
There we
Good to
go. Okay. So, my talk today is in the context of Professor Ordonez spoke a few moments ago, and basically, in one of the subsections, he spoke about microalgae-derived hydrogen. So that's the subject of my talk. It's one part of our multiple subjects collaboration, and I hope I won't take too much of your time. So the title is Maximum Microalgae-Derived Hydrogen Production in Large-Scale Photobioreactors. So I put on a slideshow. Is it okay for you, Luis?
Looking good.
Looking good? Wonderful. This is a joint work from us at UFPR and Florida State University. Here you see a picture of a schematic diagram of our sustainable research and development, Sustainable Energy Research and Development Center at UFPR. And I will be brief, but it's interesting and it's important to show in what part of our center this work fits in. So we are divided in 5 modules. Module 1 is a system of photobioreactors, large photobioreactors, each one 5, in fact, with 12 cubic meters of volume. And hydrogen could be produced directly from each of those photobioreactors. And the other modules process the biomass that is produced. Module 2 produces eventually either biodiesel or pure hydrocarbons. Module 3 uses the defatted biomass to produce necessary bioproducts so that cogeneration will make this whole project technically and economically viable or competitive with fossil fuel generated energy eventually. Module 4 consists of a power plant that is driven by the incineration of municipal solid waste. So let's focus on the production of hydrogen directly from microalgae, which is the subject of this talk. And here you see the actual image of the production of microalgae within those photobioreactors. And a brief introduction on what microalgae is due to the diversity of the audience. So microalgae are unicellular or colonial photosynthetic organisms in aquatic or humid media, and they are not a monophyletic group. That means in biology that they have had different evolution paths. So they are the so-called artificial or heterogeneous group. They do have a biotechnology potential. So I list here a few. They could be used for wastewater and emission treatment, biofuels production, such as biodiesel, as I pointed out in the previous slide, biohydrogen, also for food supplements, aquaculture, and pigments. So what were the objectives of this particular research we are talking about? The general one was the assessment of the possibility of large-scale maximum biohydrogen production. And to achieve that general objective, we listed some specific objectives. Number one, we had previous mathematical models, so we are amending the mathematical model for the so-called indirect biophotolysis process of producing hydrogen, which consists of basically two stages. One stage is aerobic, where biomass is produced, and the second stage is anaerobic, in which we collect hydrogen. So we are going to analyze cross-flow, gas production, and consumption. And the second specific objective concerns to experimental hydrogen production from green algae in the laboratory. And we use those experimental data for model adjustment and model validation, and eventually, number 5, system optimization. And to produce a model for such a large system, we needed a tool, and so we developed the tool. The tool consists of dividing the large photobioreactor in small volume elements, and we call lumped control volumes, and so this is the so-called volume element method. And that creates a three-dimensional spatial dependency, which leads us to have a system of only ordinary differential equations with respect to time, and use heat and mass transfer correlations when available, wherever available, from practical or theoretical derivation. And we consider all phases present in the process, fluid, solid, or both. And in that picture, in that figure here, you see what I'm talking about. So that is a schematic representation of the photobioreactor, and then you divide everything in small volume elements. And each volume element on the right, you see an element with culture median flow that leads to 5 unknowns, the median temperature and the mass fractions of algae, hydrogen, oxygen, and CO2 that are generated by the photosynthesis from which algae grow. And here is the description of what I told you in the previous slide, which is stage 1, in which biomass is built in. That for that stage we require the presence of air so that photosynthesis will occur. And in the second stage, in dark and photofermentation, we can produce, in the presence of this enzyme hydrogenase, the microalgae is capable of producing hydrogen. So the entire model can be summarized by those equations, reactions. And these reactions eventually break the molecule of water into hydrogen and oxygen. We write for each of the volume elements equations based on the conservation principles, basically species and energy conservation. And this is the energy conservation equation for each of those volume elements that the photobioreactor was divided, was discretized, I may say so. And conservation species is written for each of the substances that we are taking into account. So the substances of interest are the algae, the hydrogen and oxygen and CO2. And eventually that leads us to calculate those concentrations in time as the process goes. I particularly drive your attention to the equation at the bottom, and where we included a genetic modification parameter. Since typically the main problem of this process is that historically, since it was discovered in the 1930s, the production of hydrogen from microalgae is very low. So it produces a very low yield of hydrogen. So genetic modification is a way to go, so that we can eventually make this process more competitive with existing paths of producing hydrogen. So the genetic modification parameter will affect, is multiplying here, the mu H2, which is the parameter, the generation parameter in the species equation. Okay, so reaction generation parameters. It relates to the reaction kinetics. So if we have a modified, genetically modified organisms, then we can have more production. So here are the rest of the equations, and basically we applied a numerical method to solve all those equations. The PBR was divided in 6,048 volume elements, and we applied the Runge-Kutta method for 5th order with adaptive time step to obtain the solutions. And we assumed thermal equilibrium between wall and the cultivation medium, but we did not assume that the ambient temperature was constant. We varied the temperature throughout the day outside, and the concentration values calculated based on external time step showed 0.02% difference in results, and 13 minutes only of computational time versus 10 hours otherwise. So here is the aspect of the mesh and the solution, the temperature solution for the system. You can easily see that the sun is on the left side of the photobioreactor in this particular time. Here is the morphology of the algae that we used, the Tetradesmus obliquus, and we also used Chlamydomonas, which is a traditional species that is used to produce hydrogen, but we investigated Tetradesmus obliquus because it's the algae that we have in Curitiba, Paraná. So it's natural from that region. And here is on the left side, you see the Erlenmeyers with the production of with the system that produced hydrogen in those two stages of indirect biophotolysis. On the right, you see the data acquisition system, and on the right bottom, you see the hydrogen sensor that we used to monitor the production of hydrogen. Although we are confident that we wrote a reliable model, we have to prove that. So in order to do that, we adjusted the model with one set of data that we produced. And for that, we created those two constants, epsilon alga and epsilon hydrogen, and solved an inverse problem of parameter estimation to determine those constants so that the results, numerical results, matched the experimental results. Okay, and after adjustment, we used the same constants to obtain the results in a second set of data. And here you see the first for Tetradesmus obliquus. You see that the experimental is marked in purple on the graph. And on the left, on the vertical axis, you see the algae concentration, and on the horizontal axis, the time, and in 10 days of algae growth, and the variation of that parameter, the adjustment parameter. So the model is very sensitive to the variation of the parameter. So we basically obtain the value of epsilon. And here is for hydrogen production, the same procedure. And we obtained epsilon H2 with a determination coefficient of 98%. And here is for Chlamydomonas, the same procedure. And experimental validation, the second set of data, now with the determined constants, epsilon H2 and the epsilon algae. And the model actually showed good quantitative and qualitative agreement with the experimental results for the biomass growth and also for the hydrogen production. With a validated model, as we see in this picture, the numerical results on top of the experimental measurements with the sensor that I showed you a few slides ago, we agreed that the model was producing reliable results. And with that idea in mind, we formulated the optimization problem based on two objective functions: the production efficiency, which is shown there, which is how much hydrogen you produce with respect to the amount of biomass we were able to produce. And on the bottom, you see the rate of hydrogen production in the whole time of the two stages. T1 is the aerobic and T2 is the anaerobic stage. Hydrogen is produced in the anaerobic stage because the enzyme is inhibited by oxygen. So the indirect biophotolysis process is necessary for that. And here you see the final result, which shows the maximum rate of hydrogen production at a particular interval of time for the second stage, which is the anaerobic stage, in which you see that the maximum is sharp, is pronounced, and it's important to be considered if you want to maximize hydrogen production in this system. It's actually very sensitive. So we hope that these results could contribute for large-scale hydrogen production eventually in the future from this process. Genetic improvement is definitely a path to go. And here you see the microalga Chlamydomonas and several targets that could be identified, both in the mitochondria and in the chloroplast. Details would require more time to discuss, but basically the idea is that. And what to do after the optimum microalgae cultivation conditions have been reached, you think of genetic improvement. You're not satisfied. So let's do what needs to be done. So the objective is to increase the productivity of biofuels, biomass, or any other bioproduct. And the strategies are what you see typically in such a methodology, which is increasing the number of copies of a gene, increasing or decreasing the expression of one or more genes, and still the expression of heterologous genes selected from other species. And there are several transformation methods. And the DNA of interest should be cloned into vectors, and those transformation methods would insert whatever gene we want into the organism. And here is the effect, using our model, the effect of the genetic parameter. So you see a pronounced increase. Psi T equals 1 is the wild species, and the 2, 4, 10, and 14 you see what could be gained in terms of hydrogen productivity. So it's definitely a path to go, in our opinion. So the conclusions, a transient mathematical model has been developed for hydrogen production in direct biophotolysis process from microalgae. We obtained the results with low computational time, which is also important for any optimization procedure. We experimentally obtained in the laboratory hydrogen. The model was adjusted and validated with that experimental data. We were able to maximize hydrogen productivity, but there are major technical challenges to be overcome in order to make possible the industrial use of microalgae. That means genetically modified organisms in highly optimized systems will need to be developed. So this is our message. I'm still below 20 minutes. I thank Luis, and I'm open to questions.
Thank you very much, Professor Vargas, for a very nice presentation, both touching very important issues. And I'm sure that we would love to discuss both approaches, but again, we are almost 20 minutes ahead of time. So with that, I'm forced to move on. And of course, not without thanking again Dr. Ordonez for his time, and also to you, Vargas, for bringing him over, for inviting him in, and to provide such a nice overview of your research, or at least in what you are planning to do with your next projects. With this, we move on, as I said, to the next speaker. I am very happy to announce the participation or presence of Dr. Martin Mittelbach, a very good friend and also a highly respected researcher in the area of oil chemistry. So we move on from hydrogen production to hydrogen use, as he's going to speak to us a little bit about synthetic fuels. Dr. Martin Mittelbach became associate professor in 1991 and university professor in 1996 at the Institute of Chemistry of the University of Graz. He has cooperated with industry in licensing biodiesel plants, with involvement in the installation of several biodiesel plants worldwide, being responsible for the setup of quality insurance and also analysis training for local staff. Dr. Mittelbach has also been involved from the very first beginning in the development of standardization for biodiesel and also for other synthetic fuels in national and international committees. And today his research is engaged on the development of first and second generation biofuels, value-added products from non-food biomass, biorefineries, and chemical derivatization of renewable resources, particularly renewable lipids. Dr. Martin Mittelbach, are you with us?
Hello, yeah. Do you hear me?
Yes, we do. Thank you for being
Perfect.
here. It is a pleasure seeing you again, not meeting, but at least seeing you again.
At least seeing
so
each other.
Please go on and enlighten us with your presentation.
Okay, thank you very much, Luis. I'm trying to select window or screen. Okay. Do you see it?
Yes, yes.
My screen? Perfect. Then first of all, I also want to welcome you at this international meeting. It's very interesting. Congratulations, everything works perfect. So it's even better than our meetings we have in Europe. Well, it's a pleasure to be here. And I want to give, we have not so much time, but I want to give an overview about aviation fuels. It's a huge area, but I will mainly focus on lipid-based sustainable aviation fuels. As you will see, SAF. You will see some also terms which is not easy to see through about all these topics. Well, first of all, our greenhouse gas emissions, climate problems, climate warming, global warming issues, and what's the fact? So, what part aviation covers? You see, most of the CO2 emissions are coming from LDV. It's like light-duty vehicles, passenger cars. Big problem. How to handle this? Heavy-duty vehicles about 30%. Two-wheel, three-wheel. It's not so important. Marine about 11%, and aviation 10%. For all of these transport sectors, we have alternatives, especially in Europe. So 2035. We will have to change. We're not allowed to introduce combustion engines anymore in light-duty vehicles. We have alternatives. We have battery cars. For heavy duty, we have some alternatives. But for aviation, it's a good question. What can we do? Not electric planes, and therefore we have to look what could be the alternatives.
Martin,
Yes?
are you presenting your slides? I mean, your PowerPoint is not in presentation mode. So if you're moving from one slide to another, we are not seeing it.
Okay. Do you see it now?
We see slide number 3.
Yeah.
But we don't, but not in presentation mode. We still see just the file without being
the whole screen. You don't see the whole
yes, we see your screen. Yes, slide
But
3.
if you go now, you see the screen, and on the left side the slides.
Yeah, nothing is happening. When you click the presentation of your slide, nothing happens in our side.
So here I am in presentation mode.
Yeah,
Doesn't
but
work?
we don't see it.
Okay, but you see this.
We do.
So here it works.
Yeah. So if you want to go ahead and do,
I go ahead because
Yeah.
I actually don't know what's happening. But hopefully you can see. And here you see there are very ambitious goals from aviation industry, from IATA. And IATA is the International Air Transport Association, 300 members. And they have a goal, a very ambitious goal worldwide, to reach net zero emissions until 2050. What does it mean? So that's the total emissions today. And this is business as usual. And here you have until 2050, the goal is net zero emissions. What does it mean? Where could it what could they make? What could the transportation industry, aviation industry do? So you see, they could maybe have some new technologies, some new planes, 90% maybe carbon capture, but the major part would come from fuels. But what alternatives actually do we have for the aviation industry? And you see here, the goals are really enormous for these zero goals until 2050. We have now almost no sustainable aviation fuel available in the market. And here you see the amounts which have to be reached, 400 million or billion liters. It's really what European aviation industry has a goal, also very ambitious. In 2025, they want to reach 2%, and 2035, 5%. So it's very hard to reach these high amounts, but this is already agreed in the aviation industry in Europe and from the authorities. So we have a lot of abbreviations. So first of all, I want to show what is really sustainable aviation fuel. This is a drop-in, so it must meet all the specifications for jet fuel, non-fossil kerosene. It could be bio-based, it could be synthetic, but it must meet the ASTM standards, as you see here. And well, what they have to reach, of course, if it's non-fossil and renewable, it must be have very low overall emissions and very low impact, and no food crops allowed. So, if you want to use biofuels, it's very hard to reach it. Only from waste material it's possible. Then you have also the terms HVO. It means hydro-treated vegetable oils, or HEFA. These are hydroprocessed esters and fatty acids, or so-called renewable diesel, which is already well known and well established. And there is also other terms like SPK, synthetic paraffinic kerosene. Then we also heard already today Fischer-Tropsch fuels, Fischer-Tropsch synthetic kerosene, starting from CO, carbon monoxide, and hydrogen synthesis gas. Another term is e-fuels, power to liquid fuels. So that's mainly, this term mainly covers fuels which are produced directly from power or electricity coming from water via the route over hydrogen, or CO2, which could be split into carbon monoxide, and then you have the synthesis gas, but only source is electric power. And there are a lot of pathways which have been certified by ASTM for sustainable aviation fuel, 7 pathways, but only one is used today. This is so-called HEFA and HVO production, which I will cover today. Here you see the alternative routes, these 7 routes, 1, 2, 3, 4, 5, 6, 7 routes, which are certified for this drop-in jet fuel. Drop-in means it must fully meet the aviation standards, and they're very strict standards. And only one, this one, is already existing to be used in jet engine. Direct electricity, a battery, so it's not a good option, of course, for aviation industry. So coming to this route, vegetable oils, HEFA, drop-in, you see here the difference between biodiesel production. Biodiesel production means you starting from a dry glyceride, so any kind of vegetable oil, which is transformed with methanol to fatty acid methyl esters and glycerol, very well known, very well established all over the world. Biodiesel itself could not be used as aviation fuel. Even small quantities are not allowed, so it's not possible. So you have to make another route, make hydrogenation, take out all the oxygen, convert it into water, and then you get from the glycerin moiety, you get the propane, and then straight chain paraffins. These are paraffins, of course, could not be used directly as fuel because they have a very high melting point, and they have to undergo a hydroisomerization to get branched hydrocarbons. Here, in more detailed, these hydrogenation routes, there are 3 different routes. One is a decarbonylation, one is decarboxylation, and hydration is the 3rd route. All of them produce these straight chain paraffins without any oxygen, and then you have to further convert it by isomerization, by cracking into branched hydrocarbons, which have to meet these strict specification. As catalysts, a lot of routes are possible. It could be some commercial desulfurization catalysts based on nickel or molybdenum on different supports. The reaction conditions are high pressures, around 5 megapascal, and temperatures over 300 degrees. If you go to higher degrees, you have a lot of cracking and isomerization preferred at high temperatures. Looking to the chemical composition of a typical jet fuel, it's not this sustainable, it's just a common fuel. You see, it's a mixture of a lot of different products. It could be alkanes, but not so high chain lengths, isoalkanes, aromatics, and cycloalkanes. Carbon number you see here between 7 and 16. It's a lower boiling, of course, like than diesel fuel. So it's something between the gasoline and diesel, and you could adjust. You have to adjust the refining conditions to get such a mixture. You see here also the different kinds of chemical composition, N-alkanes, cycloalkanes, and alkylbenzenes. You see here density versus carbon number, and you see only these small region are meeting the specifications. So it's always a short amount which could be used as aviation fuel. So there is no chemical route or production route where you can get 100% jet fuel. It's always a small amount of your products. Here you see again the freezing point, freezing degree. It should be here in the region of -40, -50, because if it's higher temperature, of course, you can use it as aviation fuel. And here you see the product mixture of different production use. Today, we have a lot of HVO and HEFA produced by different producers worldwide. And in this normal or default procedure, you get only a small portion, about 15% of jet fuel. Then you get a lot of so-called renewable diesel, which could be used on the street for heavy duty and low duty vehicles and light ends. So maximum 15%. You can maximize this or modify the whole process up to 50%. So the optimum procedure for this HEFA production or HVO production can give you about 50% of jet fuel. For gasification, Fischer-Tropsch, you also heard about this. This is very important. It's not produced today in significant amounts worldwide. For this gasification, you could get over 20%. The maximum jet Fischer-Tropsch process could be produced maybe up to 50%. There are also other routes from alcohol to jet. Here you get more, about 80%, and isoparaffins from sugar. But also these 3 or last routes are not commercially available today. You can also get bioaviation fuel from lipids without hydrocracking. For instance, for castor oil, which contains about 50% ricinoleic acid. You can, if you make reactions up to 560 degrees, you get jet fuel by cracking and isomerization, or also the major fatty acid from oilseeds, oleic acid. You can also produce products without any oxygen, which could use directly as fuel. But these actually fuels technology are not available. What is the situation today now? Who is producing? So it's a lot of different companies are saying they want to start with aviation fuel, especially in the US. It's very hard to see. There are a series of producers which say we have projects, we have pilot plants, we have in the future. But the actually major player in Europe, but also worldwide, is Neste. It's a relatively small refining company. They have a lot of HVO production facilities in Finland, Singapore, Rotterdam, producing even today. And most of the fuel which is already used for aviation, and each airline has some trials and have some projects where they mix maybe about 2%, 5% of HVO. Most of this fuel comes from Neste Oil, but you see also UOP, Elder Fuels, and Renewable Energy Group are players in that field. But what is the production capacity outlook until 25? It's a very ambitious goal here. You see today it's almost that's the capacity, not the real production. This is HEFA production. This could be used additional if you can change the production capacity. It's 2.3 million tons, and you see the goals will show you that maybe in 25 we have a significant amount of this sustainable aviation today. If you look to production 2022, I look to this 250,000 tons, and this amount covers 0.13% of the kerosene demand of the day. So it's almost nothing. Even if you go up to these figures, it's impossible to reach 100% substitution in the next decades, I would say. If coming back to lipids, so you say for sustainable aviation fuel, food oils are not allowed. So the only way is to use waste oils, waste cooking oil especially, but the waste cooking oil has also limits. What we discovered or calculated that the maximum amount of lipid from used cooking oil are 50 million tons. You see here the red line, 50 million. Even in this year, we wouldn't have more fuel. And most of it today is used for fatty acid methyl ester for biodiesel production. And a significant amount of these waste oils are already converted into biodiesel. You could say in Europe we have a limit. We can't use all of these used cooking oil. We could use maybe a little bit this production of renewable fuel, and this is sustainable fuel. So of course you could say that waste oil could not cover the demand in the future. So you have to use also other technologies which I showed you in the beginning. So we have a fight between the feedstock, fight for waste oil feedstock today. Most of it is going. You could say what is produced today. If Neste Oil, for instance, said they produce a lot today, so it's not very hard to find out what. Well, it's not coming from waste oils. Mainly comes from waste fatty acids out of palm oil production. And that's also discussed controversially about that. But anyway, here there is a figure from Neste I found in the internet, and it's a very optimistic outlook today. So you see 40 million tons. More is not possible for waste oils because we don't have more. But what Neste looks, of course, to other feedstocks, oil trees on degraded land, oil cover crops, agricultural residues, cellulosic over forest residues, and they claim that we could cover 100% in maybe 2050. So it's very optimistic. I would say that's really we could reach it, but we have only coming from lipids, maybe 5%, 10%, they say maybe 20% could come from lipids. The rest should come from, has to come from other process technologies, from waste material, cellulosic material, and alcohol, and so on. Well, coming to the summary, which I only can show you in this overview and not in the presentation. First of all, the aviation industry has the ambitious goal for net zero emissions until 2050, as you have already seen. 65% has to be contributed from the fuels to produce sustainable aviation fuel. The only commercially available aviation fuel today is based on HEFA, made out of lipids. But only 15% of HEFA can be used as sustainable aviation fuel according to the present technology, with optimization maybe up to 50%. Today's SAF production only covers 0.13 of the global kerosene demand, so there's a lot to do in the future. The major feedstocks for SAF production today are still waste oils like used cooking oil. No food feedstocks will be accepted. And as lipid feedstocks are limited, other technologies have to be used and further developed in order to meet the demand for sustainable aviation fuel. Sources could be biomass or CO2 via Fischer-Tropsch. But in the future, also the use of other alternatives, especially liquid hydrogen, might be a realistic option to cover the really high demand of aviation fuels. With that, I want to thank you for your attention, and I'm open for questions and comments.
Thank you, Martin, for a very nice presentation, very realistic, showing the trends of this market and the need for new technologies, the shortage of raw materials that we face, and the capability of each technology to actually provide what we need in terms of sustainable fuels. Thank you so much. Without any further ado, we move on to the next speaker, as we are still a bit ahead of time. Oh, sorry, short. we are still behind our schedule. So the next speaker is Dr. Claudinei Soares Cordeiro. He has a degree in industrial chemistry from the Catholic University of Paraná, a master's degree in materials engineering from the Federal Technological University of Paraná, and a PhD in organic chemistry from the Federal University of Paraná. In addition, he has completed the postdoctoral stage or experience at the University of Idaho in the United States. And since 2009, he has been a professor at the Federal University of Paraná, where he works in the field of renewable resources chemistry, with a focus on developing heterogeneous catalysts for biomass conversion. And so, Claudinei, please welcome to the session. Thank you very much for taking our invitation, and we look forward to hearing you.
Good morning. I will share my... Can you see my screen, please?
Yes,
thank you for the invitation to speak here. And I was a visiting scholar at the University of Idaho between 2019 and 2020. And I worked in Professor Cheng's laboratory in the Department of Chemistry for the production of graphite from University of Idaho thermalized asphalt reaction, or GITAR. GITAR has been produced in Idaho for over 10 years, guitar is a material composed by a few sheets of graphene. However, some properties of guitar are different from other materials containing sp2 carbons. Guitar has been chemically modified to obtain brusted-Lowry acidity, and acid solids were used as heterogeneous catalysis in esterification reactions. The chemical modification of the solids and the esterification reactions were carried out in Professor Armando McDonald's laboratory at the College of Natural Resources. During this period, I received a scholarship from CapSprint program. All necessary infrastructure for work in the United States was provided by the University of Idaho. I'm going to talk a little about some common methods for graphene synthesis. I am also going to discuss guitar synthesis and the process to obtaining acidic solids from it. Finally, I will present some results on the performance of these acid solids in esterification reaction. Several classes of chemical compounds have been tested as heterogeneous catalysis for production of biodiesel. However,
Claudine, sorry to interrupt. Can you try to put your slides on presentation mode? Otherwise, you're facing the same problem as Martin.
okay, the first
We
slide.
we see your slides. That's for good. But the problem is that they're not in presentation mode.
Oh, okay. I will start again. Okay.
No, you don't need to start again. Just move on from where you were. All went well. The problem is that we don't see it on presentation mode. Can you try to hit the presentation mode icon down below and see whether the PowerPoint will project?
Can you see now?
Not yet.
Not yet.
Well, if it doesn't work, then you'll be forced to present from as you are, like as a slides outside of presentation mode. No. You try to share it again.
Okay, I will try.
Yeah.
Can you see now?
We see the slides. We don't have them on presentation mode, but we see the slides.
Okay. Can you see presentation mode now?
No.
Oh, I will try. 1 minute,
Yeah.
please. Can you see now?
Yes, we do. Go ahead. Thank you.
Okay. Thank you. You. Okay. Well, several classes of compounds as tested for heterogeneous catalysis for biodiesel production. However, acid catalysts can potentially be used in esterification and transesterification reactions. That is, they can be more easily adapted to the alternative process for the biodiesel production. Compounds containing sp2 carbons can be chemically modified to develop acid, brusted-Lowry acid. Such compounds have the potential to be used for production of biodiesel and the processing to glycerin. Luis, that's okay now?
Yes.
Okay. Well, the various methods for synthesized graphene can be divided in two categories: top-down destruction or bottom-up construction. I would like to draw your attention to chemical vapor deposition, as this method is used for synthesizing a material with properties similar to guitar. Chemical vapor depositions decompose hydrocarbon gases and other biomass materials to grow graphene sheet on metallic catalysts at high temperatures. as you can see in the figure. This is a sample system that was used for guitar synthesis a few years ago. The system was heated for about 50 minutes. The use of some materials for deposition of graphene is optional. This is because graphene can be deposited on the porcelain plate. The deposition temperature was estimated at 615 degrees Celsius. I would like to highlight some important aspects. In the process for the production of graphene, the deposition temperature is lower than in chemical vapor deposition. Deposition takes place in the presence of oxygen without the use of the catalyst. And the equipment used is simple. In this image, we can see the graphene sheets. I only worked with the synthesis and chemical modification of graphene. However, graphene is used in electrochemistry. There are 4 properties to distinguish graphene from other sp2 carbons, but I won't discuss them here. I recommend this article for detailed information. The material obtained by the synthesis described here has similar properties to guitar, so this material was called guitar. This is a floor shot of the equipment used for guitar synthesis using chemical vapor deposition. 3 types of supports were used: carbon black, smaller silica, and larger silica. Vegetable oils was used as a carbon source for the synthesis. The synthesis was carried out in the nitrogen atmosphere. This is a short video of the equipment in the operation during the synthesis. The synthesis time was 1 hour. All guitar samples were sulfonated. The sulfonation procedure was repeated 3 times for each samples. The solid catalysts were regenerated after use in the esterification reactions. The names of the sulfonate solids can be seen in the projection. The reactor used in the experiments did not allow for agitation. The pressure inside the reaction vessel was calculated using the Antoine equation. The GCMS was used to analyze the reaction products. The table shows the results obtained in the esterification of lauric acid with methanol without catalyst. All experiments were performed in duplicate. The arrow shows corresponds to the standard deviation. After the first cycle of use, the catalysts were recovered, regenerated, and reused in a second cycle. Therefore, the experiments correspond to the second use of the catalyst were not carried out in duplicate. The last column shows the increase in lauric acid conversion achieved with the catalyst. The sulfonate graphene used was supported on larger silica. These are the results obtained using guitar on carbon black. The results for the first use are statistically similar to the previous one. However, there was a loss of activity during the second use. The reasons for this loss of activity still need to be studied, but it may be to relate to leaching from guitar. The results of the first and second uses are similar, as with the use of larger silica. These preliminary results indicate that silica may be a better choice of support than carbon black. In these experiments, we use guitar supported on larger silica. The results shows that the solid catalyst is also active in ethyl esterification. These results demonstrate that the solid catalyst is active in the esterification reactions of lauric acid with glycerol, as shown in the table which displays the amount of unreacted lauric acid. This preliminary test showcased the potential use of the catalyst. Guitar samples were characterized by XPX, XRD, and PGA. I will not present the results because some data is not yet available. However, available data do not show change in catalysis before and after use. All the solids show activity in lauric acid esterification reactions. The results also showed that the solids can be reused. Therefore, they could be tested in alternative processes for the production of biodiesel by acid catalyst. Preliminary results also showed that they can be used to produce acylglycerides. I would like to thank you, Professors Armando and Francis, for having me in their laboratories, to Farik and Jeremy for the collaboration. I also thank the University of Idaho, UFPR, and CAPS for the scholarship. Thank you, Luis.
Thank you very much, Claudine. Very interesting catalytic system. I look forward to see future results with glycerol. Seems very interesting for that purpose as well. And yes, I'm sorry to say that we are not able to take questions today, for technical problems that we faced in the beginning. For those of you who have gathered together with us recently, we are still about 20 minutes behind the schedule, and for that reason, questions have not been able to be taken. So we move on to the next speaker. Again, Claudine, thank you very much.
Okay.
Our next speaker will be Dr. Marcio Vidotti. Dr. Marcio Vidotti holds a degree in chemistry and a PhD in physical chemistry, both from the University of São Paulo, and he has a postdoctoral experience at the State University of Campinas and also at the University of Warwick. He joined the Faculty of Chemistry at Federal University of Paraná in 2010, where he leads research activities in sensors and biosensors, electrocatalysis, nanostructured materials, and energy conversion and storage. Dr. Marcio Vidotti has agreed to replace Dr. Julie McPherson, who has been invited to join us today. Unfortunately, she was not available, actually, for problems in the time change as well. And Marcio will tell us about the research he's carrying on with her partnership. So, Marcio, please, the screen is yours.
Thank you very much, Luis. Just to be sure, my screen is showing to you?
Yes.
Okay, perfect. So, hang on. Just okay. Well, thank you very much, Luis, for your introduction. Today, I'm going to talk about this work, which is PEDOT modified electrodes for electrocatalysis and energy storage applications. As Luis has just said, this work we have the collaboration of Professor Julie McPherson from University of Warwick, Coventry, and her group, the Electrochemistry and Interfaces group. The University of Warwick is located at the West Midlands here in England. And to do the experiments, my former PhD student, Bruna, stayed in there for about 3 months. But unfortunately, to the COVID situation, she had to come back to Brazil quite earlier than expected. So she couldn't finalize the project over there. But we are running the experiments right now in Brazil to finalize this work. So when you look at the title, two words appear quite interesting for any electrochemical reason. For example, the first one here is the electrocatalysis, and the second one is the energy storage. And to run this work, we have chosen to study the electrocatalytic response of nitrophenols and nitrophenolic compounds, because these molecules, they are very dangerous to the human health, and they can be found in industrial effluents and in pesticides degradation. So it's very important how to detect and also how to remove these molecules from the environment. And a few years ago, we have developed a kind of modified electrode. Here I'm showing some results. I'm not going to go into some details about the electrochemical response, but using this modified electrode, we can see clearly the response of the 2, 3, and 4 nitrophenol towards the reduction and oxidation at this modified electrode using P dots. Clearly here, we cannot find any electrochemical response for those molecules, but using P dot, the electrocatalysis was promptly observed. And the second word I've speak before, which is the energy storage applications. So our group here in Brazil, we are deeply interested in how to build up these kind of devices to store and deliver the energy. And as any electrochemical device, it is composed by a very simple electrochemical cell containing 2 electrodes and an electrolyte in between. So our study here is how to change the surface of any electrochemical, any electrode in terms of modified electrodes to get some non-structured materials to expose this superficial area even higher, and then to get all these achievements and improvements of the electrochemical response and storage as well. So in this project, we have used the conducting polymer, the P dot, which has high conductivity, electrocatalytic properties, electroactivity, and it's possible to modify any kind of substrate. And just a little bit more of details about the P dot. Here I'm showing the structure, the chemical structure of the polymer, which has, as I said, high conductivity. And the mechanical properties for the conducting polymer is quite important, because we can change any kind of substrate with this polymer. For example, in this work, we have used some flexible electrodes, which is very important for LNG storage, but also we have used some diamond electrodes, which is very important as well for electrocatalysis. And again, not only for energy storage or electrocatalysis, the development of this new material is very important for drug delivery sensors, biosensors, engineering of tissues, and artificial muscles. So the work itself is very important, not only for these 2 applications, but for all electrochemical related applications as well. So, as I said, some years ago, we have developed a kind of new research line, which is the merge of the electrocatalysis and energy storage using this nanomaterial over here, which is the P dot nanotubes, where we can find out in this work in England, we have tried to change the substrate, because it's very important to get new physical chemical properties of this new material. Also, we have tried to do some P dot nanostructures with some different syntheses to get a very high electrocatalytic area to degrade the pollutants, as I said. And a second step we are running right now in Brazil, we are trying to get this energy, these electrons from the degradation to use elsewhere in any other kind of electrochemical device. So, as I said, we have used these boron-doped diode electrodes, which is very important for electrochemistry because it has many advantages compared with the common metallic electrodes, such as platinum and gold, and also the glass carbon. And for the second modification we have chosen to run this project is the electropolymerization of PDOT, but using surfactants as counter ions. And when you work with surfactants, it's very important to get that we can also change the concentration above and below the CMC value. So with this, we're trying to find out new morphologies of our material. And to synthesize this polymer, we have used the electrochemical profile, as you can show over here, and two different regions. They are very clearly to observe. This one in about 0.8 volts. It's very important for the oxidation of the A-dot monomer to get this polymer. As you can see here and here in these voltammogram profiles below the CMC and above the CMC. So as this potential window is achieved, you can see the second region over here. So we can observe that the electrochemical response of this modified electrode in the same time we are running the electropolymerization. So the cycles are increasing. So it's a direct evidence that we are growing up more material on the electrode surface. And studying the modified electrodes, we have tried to grow up this polymer for 3, 5, 10, and 15 cycles. So we are increasing the thickness of the material, the electrocatalytic material. And here are the results for the materials synthesized below the CMC and above the CMC. It's very important to observe that the electrochemical response, they are quite different, but we are talking about the very same electrocatalytic material. So it's quite interesting to study a little bit further why these changes are occurring. So to get more information about this interface, we have done the SCM images of the modified electrodes. Here is the electrode modified for only 3 cycles of polymeric growth. We can observe these very low aggregates here, but increasing the number of cycles, clearly we can observe as well the increasing of these agglomerates, reaching out a very porous structure containing some globular structures in the nanometric region. We have done the very same study for the 20 millimolar of DBS, which is above the CMC, and we see that for 3 cycles, instead of observing this kind of aggregates, we observe a thin film layer and the presence of those structures here which are not observed in literature so far. So, because when you use these above the CMC, normally you observe some round structures, but in this case, they are kind of flat, more similar to a leaf. And it's a very surprising for us to observe this kind of structure. And by increasing the polymerization of the material, we can observe that a very different structure or morphology is observed compared with the material electropolymerized without these templates. And took a little bit observation with more details about this material, we can observe for 15 cycles this porous structure, as I showed before, and in the presence of those structures of the DBS, we can observe a kind of thin plate is being formed with the PDOT growing exactly on this kind of horns. I don't know how to say the word for that, but it's quite interesting because it forms a kind, really a template for the growth of the PDOT. And that's the reason why we have so different electrochemical response, as I showed before. And to study the catalytical performance of the electrode, we have done the voltammograms of the material, as I said, and we have shown that the capacitive current of this kind of electrode compared to this one, we observe that in the presence of these templates, the capacitive current increases increases higher compared with this one, because somehow these structures allows the higher energetic surface interfaces. So the capacitive current, which is related to the double layer structure, somehow is enhanced in the presence of the polymeric structures growth on the templates. But on the other hand, when we observed the electrocatalytic response towards the oxidation and reduction of the 4-nitrophenol, we observe that the response is a little bit different. And if we look with more details, we observe that the use of the 1 millimolar DBS due to this porous structure somehow is more electrocatalytic compared to the structure which are formed in the presence in the template structure. Somehow, we're not quite sure yet why this happened, because we are studying, as I said, we are studying right now this kind of behavior using other techniques that somehow these the electrocatalytic active sites are more available for the oxidation of 4-nitrophenol to aminophenol compared with these modified electrodes. So this was the work done in England with Bruna, but now we were trying to adapt this kind of methodology to get, as I said before, the merge of the electrocatalysis and the energy storage. So we are planning at the same time to remove these pollutants and under continuous cycling to get the higher energy under a very, very high current for the application. So if we compare, for example, these results I showed in the lab publication I showed before, the increase of the capacity of rotation or the charge transfer between the electrodes, they increase it very, very highly compared with no presence of the pollutants, which indicates that in fact we are getting the energy or the electrons from these pollutants and really getting this energy to do something more important. Well, I hope I get the time right. I need to thank you all the agencies for the support, in special Professor Julie McPherson and Dr. Alexandra Borrow for all the help in experiments in England with Bruna, and all the print copies, which was possible for the funding for the travel and assistance of Bruna. And thank you very much for your attention to watch this presentation. Thank you very much, Luis.
Thank you very much, Marcio, for keeping the time and for giving us such an interesting talk. I don't know how many times I have already mentioned it, but we are not been able to open the floor for questions.
Sure.
Thank you again for this and for covering your partner in this presentation. So I believe that the next presentation will be given to a student of yours. So that will be an opportunity to extend our knowledge about the research activities that you're developing at UFPR. So, having said that, I have the pleasure to introduce you to Gabriela, who have misspelled her name. So sorry about that, Gabriela, in the program, of course. But Gabriela Tonnet is a chemical engineer, graduated at UFPR. She has a master's degree in chemistry from UFPR and is now in the final year of her PhD in chemistry. In 2021, she had the opportunity to spend a year at the University of Vigo under the CAP Sprint program, working on a research project on smart nanomaterials for energy applications. Gabriela, thank you very much for taking our invitation. It is a pleasure to have you here. The screen is yours.
Thank you, Luis. I will share my screen now. Hope it will work. Can you see my presentation?
Yes, we do, Gabriela. Go ahead.
Okay. So as you mentioned, I am working with my PhD project with Professor Marcio Vidotti. So I will be continuing a little bit on a different project, but more or less on what he was already talking to you about. And I will be talking today a bit about electroactive and stimuli responsive polypyrrole linseed oil nanocapsules, which is the main focus of my PhD. And is also the project that I developed under my time in the University of Vigo. So just for you to be a little, to know where I was, the University of Vigo is all in the north part of Spain, really close to Portugal. And it's a very modern university, which is focused a lot on research. And they have a center, which is the Symbio, dedicated only to research of nanomaterials. And inside Symbio, I was located in the colloid chemistry group under the supervision of Professor Isabel Pastoriza and Professor Jorge Juste that lead this research group. And in my time there, I was working with a nanomaterial that can be applicable for renewable energy applications. And as many of you know, and Professor Marcio already told you a little bit about, we need some special characteristics of materials that are interesting for energy applications. And I will be focusing on two of them, which is the material has to be electroactive. And of course, a high surface area is also interesting, as you saw in those porous structures that he showed you in the previous presentation. So that's why we go into the nanoscale and try to form nanomaterials, mainly to attend these two important characteristics. So on my project specifically, I am working with nanocapsules. And for these nanocapsules, I have a shell material, the conducting polymers, which are the electroactive ingredient that are interesting for these applications. And I work with polypyrrole, which has similar properties as PEDOT, which Professor Marcio already told you a little bit about. And as nuclei material, I use linseed oil, which is a natural oil obtained from linseed. And its properties are interesting because he's a self-drying oil, and this property can be used for self-healing applications. So they are both considered smart materials. A little bit more about the conducting polymer, which you already saw. We have many different polymers that were developed since the discovery of polyacetylene, which was the first conducting polymer. And they have a property that I will be exploring in this project, which is a variable conductivity depending on their redox state, if it's oxidized or reduced. And these changes in the redox state are associated with changing in other properties of the material. And one of them, which is explored for these capsules, is the electrochemomechanical deformation. So if you imagine a conducting polymer with an anion, which is immobilized in its matrix, such as SDBS, which is the surfactant that Professor Marcio talked to you about, once we have this kind of structure and we reduce this polymer, we need to maintain electroneutrality inside the polymeric matrix. So in this case, cations are incorporated into the polymer to maintain this electroneutrality, this equilibrium. And this process is, of course, reversible. So what we observe is a change in the volume of the polymer associated with the oxidation and reduction. And in this case, we are working with the polymer as a cation exchanger. So this property is useful to form a capsule because if we construct the capsule, the nanocapsule, with this polymer as the shell material, what it means is that the reduction of the shell and incorporating of the cation will result in a shell expansion of the capsule, which would be useful to release whatever material you have encapsulated. And again, this would be a reversible process, and we could revert this and close the capsule upon giving it a stimuli. So this is what classified these materials as stimuli responsive, and is a controlled release mechanism, which is what we are interested in this project. So the methodology to make these nanocapsules was emulsion polymerization. Since we are working with the oil, we use this linseed oil to form an emulsion, and we trap the monomer, the pyrrole, inside the oil phase before emulsion formation. Then we add the surfactant, the SDBS, and as a following step, we add the oxidizer or the initiator that will promote the polymerization of this monomer, which is trapped inside the oil core. And then this will force the polymerization to happen at the interface, at the oil-water interface, forming the capsule shell. So this is the main strategy, but experimentally, this is done by adding all the ingredients, linseed oil, the monomer, the surfactant, and water to a glassware. It's constructed especially for these synthesis. And we use an ultrasonicator to form a nanoemulsion, because this will offer enough energy for us to disperse the oil in droplets that are small enough to reach the nanoscale. Then we simply add them to a mixer, and with a slow stir, we add liquids of the oxidizing agent solution, and this will form the capsules. Then we wash these capsules and go into the analysis, which is what I will be showing to you now. So for the polypyro capsules, we first analyzed how many ultrasound cycles were enough for us to reach the nanoscale. So we determined that with 10 cycles of ultrasonication, 10 cycles of 1 minute, we could reach sizes around 160 nanometers and a low polydispersity of the oil droplets below 0.2. So as a following step, we studied the influence of the concentration and the type of oxidizing agent on the morphology of the capsules. And we started by using ammonium persulfate, which is a common oxidizer to form polypyrrole. And we used 2 different concentrations. And we saw that, as expected, the more concentrated solution formed slightly bigger capsules. This trend was confirmed also with DLS measurements. So we measured the capsule size in TEM images and in DLS, and comparing those 2 measurements, they were in agreement. We could also see that the zeta potential of these capsules was negative, which is confirmation that the SDBS surfactant is being incorporated into the polymeric matrix. And then we moved to use a different oxidizing agent, which is iron chloride, and we observed the same trend with 3 different concentrations. So the more oxidizer, the more concentrated is the oxidizer. The bigger we get the capsule, so we are actually promoting formation of thicker shells of the capsules, but roughly they have all the same morphology and integrity. Again, the results of measurements of TEM and DLS were in agreement, and we also observed that for these different oxidizer, we have still the incorporation of the SDBS, as we can confirm from the zeta potential measurements. So this work was all performed during my year abroad in Spain, And then part of this work was performed in Spain, and part is what I'm finishing now that I have returned to Brazil. This next step was actually to be able to prove if the capsules would open and close upon a stimuli, upon a controlled stimulus. And we chose two types of stimuli. One, where the capsules would be submitted to reducing and oxidizing solutions. So this would be done colloidally with the capsules dispersed in solution. And we actually formed a solution that would open and one solution that would close the capsules. This part was performed in Spain. And then the next step, which is what I'm doing right now, is to repeat this open and closing of the capsules, but electrochemically, by immobilizing these capsules in an electrode and then oxidizing and reducing them electrochemically. So basically, just to remind you that example, we have a capsule with polypyro and DBS. And when we reduce this and incorporate a cation, and then we have the expansion of the shell and release of in this case, the linseed oil. And then this process should be reversible once we oxidize the capsule again. So far, we see that when we subject the capsules to an open solution, which is the solution that reduces the shell, we can see the oil leakage from the capsule nuclei in the TEM images, and also a decreasing contrast on the area that should be the capsule, which indicates that the material is escaping, is leaving the capsule nuclei and actually being released in the media. This was also done with compared to the untreated capsules, which has no leakage material, but they were also treated only with the electrolyte and with the solution that's supposed to close them. And we have seen no significant changes, which means that this polymer is being only responsive to the open solution, the reducing solution, which suggests that it does indeed have a stimuli responsive behavior. Then we also submitted these capsules to AFM, and we could also see that we have remains of linseed oil leaking from the capsules in comparison with the closed solution. Nothing happens. And most importantly, the AFM gave us an idea on how this oil is leaking. And we see this formation of spherical structures in the top of the capsules, which were treated with the open solution, that have a diameter of 10 to 30 nanometers. And this does not appear in any other capsule. This indicates that once that the shell is expanding, we are forming preferred paths for the leakage of the linseed oil. And as I mentioned in the beginning of the presentation, this oil is a drying oil. So once it gets in touch with oxygen, it dries and forms a solid film. So what we are seeing here is that the oil was leaked, and then it formed a film around the capsules into these preferred paths. And for me to wrap up real quickly, future work includes expanding this synthesis for other conducting polymers, such as PEDOT, which Professor Marcia showed you in the previous presentations, very interesting conducting polymer for many applications. Then we intend evaluating better these self-healing properties of the linseed oil and how we could employ them in electrochemical devices. Then actually incorporating these capsules into devices, seeing what possible applications we could have for them. And finally, of course, the goal would be real-life applications where we test these nanocapsules for applications such as corrosion prevention layers, intelligent layers that can self-repair once they are once they start having a corrosion current, they would automatically self-heal with this mechanism of the polymer combined with the oil, and then stop the corrosion in an intelligent manner. So then I want to thank you all so much for your attention, and I would of course like to thank all the groups that are part of this research, and also CAPES and the CAPES print program that allowed me to spend a year abroad. That was so important to the development of this work. And then thank you all so much for the opportunity of presenting my work here and for your attention.
Thank you very much, Gabriela, for such a mature presentation, very nicely given, excellent contents.
Thank you.
Very impressive.
Thank you.
Congratulations. But since we are again behind the schedule, we have to move on.
Sure.
And now we go to the very last topic of our workshop. We have the pleasure of having Dr. Ziao Taobi from the University of British Columbia with us today. Dr. Ziao Taobi is the Methonex Professor in Clean Energy Systems at the Department of Chemical and Biological Engineering of UBC, and also the Director of the Clean Energy Research Center at the same university. He is a Fellow of the Canadian Academy of Engineering, and his research is focused on particle technology, fluidized bed reactors for biomass thermal catalytic conversion, life cycle analysis, and integrated assessment of clean energy systems. Dr. B received one of our students during a one-year stay in Vancouver, and I am grateful for the high treatment she had while in Vancouver. And of course, it was an honor for us to have you involved in this research, Dr. B, and thank you very much for accepting our invitation and for being up so early in the morning, because I believe that you guys in Vancouver are several hours behind us. So thank you very much. Please go ahead.
Thank you.
Thank you.
Thank you. I want to check everyone can see my screen in presentation mode.
Not yet in presentation mode. We see your screen, but we don't have it in presentation mode.
Maybe I should try one more time to share my screen. How about this time?
Now we don't see the PowerPoint. We are probably seeing your screen, but not the PowerPoint.
Yeah, I think I have some difficulty as the previous.
It's okay. I mean, I had the same trouble in the morning, when we started the session. So,
So let me see. Share window or entire screen. Okay. Now let me try this time. No, I cannot share the. Can you see my presentation, but not in the presentation mode?
Yeah, we see the presentation, but not in presentation mode.
Let me try again one more time. Can you see the presentation mode?
Not yet.
Not yet. Okay, I think I gave up. Okay, let me just go this way. I do not want to hold people. Okay, so let me go this way. Sure. So first of all, thank you very much, everyone, for inviting me to attend this event. I think this is really a unique event. So I will give my first presentation, give an overview about what we are doing, and then what our the strategy, then followed by student Julianne will give a presentation about her research carried out at the University of British Columbia. So let me start my presentation. I want to talk about the deep decarbonization strategies of the waste biomass energy systems. So I will give you a brief introduction. Then I will talk about our view how to maximize the greenhouse gas reduction by optimizing the biomass utilization pathways. Then I will talk about how to further maximize the bioenergy GHG reduction potential by capturing the biogenic CO2 or biogenic carbon from the bioenergy. So first of all, I want to give you an overview. Of course, the energy portfolio varies from country to country. I think, say, in Brazil and in Canada, we may have different energy structure. So this is one of the analysis we carried out for our particular British Columbia, a province in Canada. So in Canada, we have a 40% reduction target by 2030 to be below 2007 level of the greenhouse gas emissions. So that translates into about 26 million tons of the CO2 equivalent need to be reduced on a yearly basis. So we did kind of the energy demand and supply analysis. On the right side is energy demand by 2030 based on the forecast of the energy growth in Canada. Also, the government policies. For example, we want to electrify 80% of our transportation system, and also we want to decarbonize our energy or carbon content in our gasoline, the diesel, and so on. So based on those analysis, this is the demand on the right side. Then we match the demand to see what is the supply side, what kind of energy we need. So if you look into the left side, very, very interesting. We continue to use the gasoline or the fossil crude oil. Also, we continue to use the natural gas. So overall, 40% of our energy will still come from the fossil basis by 2030. But where are the low carbon or renewable energy sources we can count on? One is the electricity. So here shows the current electricity, but to meet the 2030 target, we need another 41.9 petajoule of electricity. It's about 20% more electricity need to be generated. Then the second largest renewable energy sources in Canada or in British Columbia is the bioenergy. So these are the what available, but to meet our 2030 demand, we again need another about 20% of additional supply of the bioenergy or biofuels, which is not available or is not really now is not available from our supply system. So it really shows we will have a shortage of the renewable energy sources by 2030. So we need to prioritize our use of electricity and then the biofuels, or try to improve the efficiency of those energy use. So that comes with the research question, say, if we have the biomass, so it can be used for the heating to displace, say, the natural gas for the heating, or can be used to produce the biofuels, which can be used to displace the gasoline diesel, or for electricity generation to to power our electrical grid, or to make into the biohydrogen that will support the hydrogen economy. But which way or which pathway will be a better pathway? So that is really our research question: how to maximize the greenhouse gas reduction potential from our available waste biomass. In our university or in my group, I have been doing a lot of the bioenergy research, from the biomass gasification to biomass pyrolysis, and then wood pellet production, as well as the biogas production. So we want to see what will be a better pathway if decarbonization has the highest priority, for example, to meet our 2030 target. So first one we look into is what pathway will be better. So in that case, we analyze the biomass from the forests, biomass, or from the agricultural biomass or the municipal biomass, Then we will collect it and so on. So we examine these pathways for gasification to make the syngas. That is one of the research activity in our group. Then the syngas can be used combustion for the heat and power generation, or can be converted to the methanol or ethanol or the biomethane. Then displace different kind of the fossil fuels. Or the biomass can be pyrolyzed to make the bio oil, and then upgrade to the biogasoline or the overall liquid biofuels, and then replace the fossil liquid fuels. So how to quantify the decarbonization potential of different bioenergy conversion pathways? We look into here. So if you take the waste biomass, the reference case or the conventional practice in British Columbia is when we have the forest harvesting residuals, we have to be collected to the roadside, and then we have to burn it. The reason is we cannot leave them in the forest, otherwise it can cause the forest fire a problem. So the current practice is roadside burning. So you collect the residuals to the roadside and then burn to minimize the residuals accumulating in the forest. So we set this one as the base case. When you burn the biomass, you will release the greenhouse gas, W1. Then now we talk about bioenergy. So we collect those residuals, then to process it into the biofuels. Then we burn the biofuels. Of course, the biofuels will displace the fossil fuels. So these are the emissions from the processing of the biomass, from the burning of the biomass. But this is the credit or the reduced greenhouse gas emissions from the displaced fossil fuels. So the net greenhouse gas emission reduction will be the credit from the avoided roadside burning and the avoided the fossil fuel use, and then minus the emissions from the processing and combustion of the biomass. So this is the way we quantify the greenhouse gas emission reduction potential for each type of the bioenergy application pathways. So I will skip all these details, how to do this life cycle analysis. I will just share with you some of the observations from this analysis. So what we reported here is for each ton of the waste biomass. So we want to see is for each given amount of the feedstock, in this case is dry biomass, how much of the greenhouse gas emission can be reduced. So this is a kilogram CO2 equivalent per dry ton of the biomass. So look into here, we can see two options. One is to use the biomass directly for the burning to provide the heat for the district heating or residential heating or industrial heating, have a highest GHG reduction potential. That is this shaded white area. Then the second highest reduction potential is to convert the biomass to liquid biofuels, then have a second highest reduction potential, then followed by the biomethanol production, bioethanol production, renewable natural gas production, or combined heat and power generation. The least reduction potential is to combust the biomass to make the power, because in our province, most of the power is generated from the hydro power stations. So it already has very, very low carbon intensity. To displace the hydropower using the biopower is not going to reduce the greenhouse gas emissions. So fundamentally, the favored pathways to maximize the greenhouse gas reduction is the biomass for the heating or biomass for the liquid biofuel production. How about the cost? Also, we look into the minimum selling price per gigajoule of this bioenergy. So you can see the green kind of the bar represent the fossil fuels. In this case, is the biomass heating displaced the natural gas heating. Actually, cost-wise, is quite similar now. So it means it's competitive now. How about the second option? That is for making the liquid biofuels compared to the fossil liquid fuels is still more expensive. So this is the reduction potential, and then the GHG reduction potential, and then cost. So this is our recommendation for our kind of the government. The first recommendation is we should develop the policies to support the transition for the bioenergy deployment for the industrial district and the residential heating. so to replace the natural gas. This will be beneficial over the short term because we do not have liquid biofuel technologies still expensive for deployment now. Also, this will give us the highest reduction potential of the greenhouse gas emission. The second observation is to develop the high efficiency and low cost conversion technologies to produce liquid biofuels for long distance transportation, but that can be done over the medium to the long term. For example, for us to prepare to meet the 2050 carbon neutral target. So these are the recommendations based on our kind of the biomass utilization pathway analysis. So another question is, as I said, is we still have a shortage of the biomass supply. Even we prioritize our biomass utilization towards the maximizing the GHG reduction, we still need to think about how to further reduce the greenhouse gas emissions using our available biomass. So since you remember, we said we will have a shortage of supply. So we'll also examine how to further kind of increase the decarbonization. So we try to think about is capturing the biogenic carbon. So that is we call it the bioenergy combined with carbon capture and sequestration. So in here, I show you a diagram. Is this is all these decarbonization technologies. Looking to this side, mostly are the natural-based solutions, like using the biochar and the forest and so on. But this is the bioenergy with the carbon capture and utilization. You can see the cost of the per ton of the CO2 capture is reasonably low. It's lower than $100 per ton of the CO2. This side is we call it the electrical fuels, like the convert the CO2, capture CO2 and convert them to the algae and different liquid fuels. It's still quite expensive in terms of the per ton CO2 capture. So looking into this IRENA, International Renewable Energy Agency, this is the prediction. Is the carbon capture will be definitely playing an important role, account for about 20% of the contribution to the greenhouse gas emission reduction. But look into here, this is a fossil fuel-based CO2 capture. This is a renewable energy-based CO2 capture. So clearly we can see the International Renewable Energy Agency bet on a significant contribution from the bioenergy-based carbon capture and storage technologies. So that is the one we want to evaluate. So again, I will bring you to your attention is when we have the biomass or waste biomass, we have two pathways to do the gasification or do the pyrolysis. In the gasification pathway, we make the combustion, methanation to make the renewable natural gas or make the liquid fuels. We can have different kind of the locations to capture the CO2, either the post-combustion or pre-conversion. For example, if you do the methanation, you can capture CO2 before you do the methanation. If you do the conversion to the biohydrogen, again, you can separate the CO2 before you burn the hydrogen. So there are different ways to capture the CO2, but also look into the pyrolysis pathways. You make the liquid biofuels, but also you produce the biochar. These are the biogenic carbons. So if you can use the biochar as the sequestration approach, also you can capture the biogenic carbon. So we examine different pathways again to see how can we further deepen the greenhouse gas emission reductions. So this shows you the result based on the life cycle analysis about 3 different products we produce. One is the syngas, that is just from the gasification. We produce the clean syngas. The clean syngas can be directly burned for the energy production, for example. Then in this case, we compare the syngas production without CO2 capture and the syngas production with the carbon capture, with the CO2 capture. You can see this is the net reduction with the CO2 capture compared to without CO2 capture. This is the renewable natural gas, again, without CO2 capture, this is with the CO2 capture. This is the biohydrogen without the CO2 capture, this is with the CO2 capture. Clearly you can see the biohydrogen production with the CO2 capture will give you the highest GHG reduction potential, because the hydrogen doesn't contain the carbon anymore. All the biogenic carbon in this case has been captured, right? But then followed by the RNG, and then syngas has the lowest GHG reduction potential. But how about the economics? It's very, very interesting to see which one will be economically viable. Again, looking into the syngas, this is the net cost or minimum selling price of the syngas. This is the biohydrogen. This is the renewable natural gas. The syngas has a lowest decarbonization potential, but also it has the lowest cost to be produced. Hydrogen and then renewable natural gas has the higher decarbonization potential, but more expensive to be produced. So just to give you a rough idea here, the commercial price of the green hydrogen now is about $25 per gigajoule. From our analysis here, from the biomass-based biohydrogen, it's about $30 per gigajoule. So it's still more expensive compared to what is currently green hydrogen is produced. So that is the gas fuels from this with the CO2 capture. So we also look into the biomass pyrolysis. If you produce the liquid biofuels, but same time produce the biochar, you can use the biochar for the carbon sequestration. So with the biochar for sequestration, we analyze the scenarios. So this is the reference case. It's the fossil fuel derived liquid fuels. This is the biofuels derived from the pyrolysis with the biochar credit given. So you can see again, it's a negative carbon emissions. It's a negative 57.6. So I remind you, if you compare to the gas fuels we produce here, you can see it's very, very similar order. That one's 57. Here's anywhere from 40 to 84. These are the gases biofuels. This is the liquid biofuels with the biochar captured for the CO2 sequestration, right? So again, it shows a promise of those bioenergy technologies coupled with the carbon capture and then sequestration. So this is our recommendation. Is capture of the biogenic carbon or CO2 will enable negative bioenergy technologies for deep reduction of the greenhouse gas emissions of the bioenergy systems. And because of the easy storage and the broad application potentials, we believe biochar co-production from pyrolysis or cracking should be prioritized, because the CO2 capture has been broadly practiced, or the technology is there, but the CO2 storage or secure storage and the CO2 utilization is still very, very challenging, right? You need to find kind of the deep reservoir to store the CO2 securely, or as I showed you in previous slide, to convert the CO2 to electro fuels is still very, very expensive compared to the biochar. So that is my presentation I want to share with you. So thank you very much for your attention.
Sorry about that. Thank you very much, Dr. B, for such a nice presentation, well fit to the other subjects of our workshop. The importance of carbon capture in the form of CO2 and its use as well is very high if we want to meet the demands of the Paris Agreement and other agreements coming afterwards. So we're pleased to have you here today, and I enjoyed very much your approach. So let us now move on to hearing a little bit about the results obtained with your group. Dr. Maria Juliane Suota, she spent 1 year at Dr. B's lab in Vancouver. And she came from a PhD then at the graduate program in chemistry at the Federal University of Paraná, finished in 2022. and she works with microwave-assisted pyrolysis in partnership with Dr. B's group in Vancouver. And her main research activities or interests are related to producing and characterizing bio-oils from oil-bearing materials and also lignocellulosic materials, and this using, of course, thermal conversion processes. Giuliani, please, the floor is yours.
I will share my screen.
Okay.
Can you see my screen in presentation
Yes, we
mode?
do.
Okay. So good morning, everyone. Thank you, Professor Luis, for the presentation, for the introduction. And good morning, Dr. B. It's always a pleasure to connect with you again. And today I'm very proud to share some of those results we got together at the UBC last year. So I have selected some results and I will approach some things about catalytic microwave assisted pyrolysis of lignophorous lignins. So this is the skeletal view of my presentation. I will share a little bit about my background here in Brazil before traveling to Canada. And further, I will bring some results about the exchange concerning lignin depolymerization in your facilities. May I start with lignin? So lignin is a very available material in the plant cell wall. As we can see here, these yellowish blocks are binding the cellulose fibers and hemicellulose chains together. And lignin protect the carbohydrates against fungi, moisture, and UV light, and also against microbial and chemical attack. Lignin is highly produced in the pulp and paper industries, but all the lignin, or a great part of this lignin, is converted in power and steam in energy in situ. So in this process, the wood chips from lignocellulosic materials are digested and release the lignin in a soluble way. And this material is usually converted in energy. Today, the things are changing, and some initiatives are worried about using lignin for another applications. So in this case, lignophorous system was developed to remove lignin from the craft process and using this lignin as a precursor for biofuels, biomaterials, biopolymers after several steps that precipitates lignin and deliver it in a form of dry powder. So it's important to say that lignin can contain up to 40% on a dry basis in the lignocellulosic materials. And also, it's important to say that our Brazilian forestry sector is very prominent. We produce around 9 million hectares of planted trees, and this represents virtually unexplored source of lignin and renewable carbon. Lignin varies a lot in the nature, so softwoods, hardwoods, and grasses, they have different composition of lignin because the monolignose in their composition are different. And not only the structure can vary according to the species, but the isolation process is very intense and can change and modify, making some modifications in the lignin structure. This is why it's really hard to determine the properties of lignin. This is the reason why I spent more or less 2 years doing the lignin characterization before traveling to Canada for finishing my experimental set. So I performed here in Brazil compositional, structural, thermal, and wet analysis to determine the composition and properties of the lignophorous lignins coming from the lignophorous process. This was a very hard work before thinking about converting lignin into small molecular weight compounds. So once I did this, I spent around a year in Canada, and I was mainly interested in lignin depolymerization using pyrolysis strategies. In this case, I was using microwave-assisted pyrolysis. And why I have chosen Canada? So we know that Canada has a very expressive forestry activity. So it was very convenient, chose Canada as a country to spend part of the research. And in addition, UBC is ranked among one of the 20 best public university around the world. And thousands of students come from around the world to study at UBC. And UBC is located in Vancouver, which is considered one of the most sustainable cities around the world. So I was craving for having this experience, considering I could finish my PhD in a place like that. Let me reintroduce Dr. B, if I may. So Dr. B is a director of the Clean Energy and Research Center, and also a professor at the Chemical and Biological Engineering. And I have no words to describe how important was being part of your research group. But I imagine that your age index can say a lot about the impact of your research in Canada and around the world. And I would say that our interests were and are super aligned concerning green energy or green engineering, clean energy, and sustainability. And being part of your research group enable finishing this set of experiments I was intending to do while I was here in Brazil. So I have chosen your research group considering the possibility of converting lignin into small molecular weight products. And it's important to highlight that Dr. B is a researcher award in bioenergy sector. So this is so important for our research group and our collaboration. In the Dr. B's research group, I was supported by previous students, and especially Mohammed and Morriside, and both had background about converting biomass into small molecular weight compounds, and also into biochar. So my main interests were producing bio-oil and biochar using different catalysts, such as clinoptilolite, a kind of natural zeolite, and also K3PO4. And we were expecting higher bio-oil production using the zeolite and a cleaner biochar using K3PO4. Since K3PO4 is washable, so it was possible producing it and later washing with water and having a cleaner biochar. The system I was using at UBC, University of British Columbia, was a microwave-assisted reactor. This system is famous or has several advantages concerning the time of the pyrolysis. because usually conventional pyrolysis takes time and spend energy. And in this case, we could perform some pyrolysis experiments in shorter times, for example, 20 or 25 minutes, and producing liquids, as we can see here, and solids, as we can see here, and the gas. At that moment, I haven't collected the gas for analysis, but pyrolysis is a very promising reaction where we can obtain from biomass solids, liquids, and gas, and for further using it in several applications. So here in this tube, this reactor, we can see the lignin mixed with the catalyst in an uniform way. We can't separate both. And this material was placed in this area and irradiated with microwave energy. After 20 minutes, around 25 minutes, we collect all these materials for analysis. So I will have worked in 2 different projects, and using K3PO4, I was monitoring the heating of the process here, and we can see how high is the heating rate here. In less than 5 minutes, we reach high temperatures around 450 degrees. This process generated solid, liquid, and gas, or biochar, bio-oil, and pyrolysis gas, and the biochar was the main product of this pyrolysis reaction. After this step, we decided to characterize this biochar, performing scanning electron microscopy, FTIR, PET for analysis of the surface area, and X-ray diffraction for monitoring the crystallinity, and also the elemental composition and ash composition. Those results were super promising. As we can see here, both biochar coming from softwood lignin and hardwood lignin, they were rich in carbon. And as Dr. B said before, synthesizing biochar, it's a wonderful way to store carbon and decrease the warming global problems. So we can use biochar this way, or even in another strategies I will show you later. And here, after XRD analysis, we identify any crystallinity in this biochar. It's a totally amorphous material, which is not bad, considering it is a biochar. After the BET analysis, we observed a very significant surface area, around 200 square meters per gram for softwood biochar and 140 for hardwood biochar. So this was a promising result, considering the biochar was not improved with any activation process. And also we could see here the micropores and pores are classified into micropores and mesopores according to the UPAC. In addition, the FTIR showed the degradation of functional groups present in original biomass. We usually have a high hydroxyl band here, and after the pyrolysis process, this band highly decrease after the process. And finally, after scanning electron microscopy, we could see the pore structure of this material. And we can identify here several roles and irregularities, and this is an indicative of having a good adsorption properties. After this characterization, we went further and we decided to test the absorption capacity of those biochars. And we have chosen methylene blue as a molecule, a model molecule. And here, down here, we can see how efficient was a lower concentration of biochar is able to remove almost all the molecules or the concentration of the solution, which is a very promising result considering the environmental aspects. Later, we analyzed the adsorption efficiency, which was close to 100%, and the adsorption capacity was close to 15 milligrams per gram of biochar, which is very consistent with the literature, considering this biochar was not activated or improved with any improvement process. All these results in the first project generate enough data for producing a paper, which is in final writing stage. And this paper will be is a collaboration of UFPR, UBC, and University of the Basque Country. This university, it's included in this work because I have the pleasure to meet a professor, a visitor professor over there, and he was helping me with the adsorption tests, and he collaborates with us in these studies. We are also very happy because our work was accepted for oral presentation in the World Congress of Chemical Engineering that will be held in Buenos Aires in June. The second part of the experiments, I was replacing the catalyst for zeolite, and in this case, we have produced biochar and bio-oil using those conditions showed here. So we have produced biochar at 350, 450, and 550, and also bio-oil and pyrolysis gas. And also we could change the concentration of catalyst in this process. I forgot to say that clinopetylolite and K3PO4 both act as catalyst and microwave energy absorbers. So they increase the heat inside the system, promoting high heating rates and also helping to depolymerizate the biomass or lignin into small molecular weight because the heat is intensified inside the system. Those biochars produced by this strategy, they are in characterization phase here in Brazil. I haven't had time to finish this step there because my time was over. And the bio-oil was characterized by GCMS, and in general, the yield was around 36% of liquids, including bio-oil around 17% and an aqueous phase 19%. This is why, because the pyrolysis liquids coming from lignin pyrolysis, it's not homogeneous, so this material form phases, and I consider 17% bio-oil and aqueous phase, and 31% of solids, an average, and also around 32% of gases. In here we can see the view of the compounds. So the bio-oil is shown here with phenol and cresols and another compounds here. And the aqueous phase for softwood lignin pyrolysis with a different composition here. In this composition, we can see we found phenol, cresols, guaiacol, which have a great commercial interest, and they can be applied as antioxidants or monomers for biopolymers and aromatic compounds, which are precursors for fuel additives and also aviation fuels as well. My experience at UBC was incredible, amazing. I think we create a link between UFPR and UBC. I was immersed in a very interesting culture and very familiar culture. Living in Vancouver was inspirational. That was a city leader in climate change and sustainability, so it was a pleasure living there. I consider that I got some personal developments in terms of life experience and autonomy and self-knowledge. My curriculum was really improved with this experience because we will publish 1 or 2 papers considering this experience there, and we did an international collaboration, and I could improve my English skills as well. Oh, sorry. And I am so thankful to CapSprint for strengthening the ties between UFPR and UBC. So I would like to say thank you to UFPR and UBC, the CapSprint program, CAPES and CNPq, and this is a little bit about what I was living there. This is UBC campus in fall season and Thanksgiving. I was working in the lab and using a bike to go to the campus. And thank you very much for your attention.
Thank you, Juliane, for a very nice presentation, giving a little bit of your experience as well, insights of your time in Vancouver. This is also very important to motivate our students to enroll in the same type of experience. Yes, you have helped strengthening the bonds with UBC. As you know, I have myself worked at UBC as a PhD student long time ago, and I agree with you. There aren't many better places in the world to be. In terms of in the environment and at the university, very nice, and the campus is fantastic. The city is amazing. So it's very nice that you had a good time in there. Of course, thanks to Dr. B for having you and also for helping you with your research. Well, we are about 20 minutes late in our schedule. I can only thank you all for staying with us up until the end of this workshop. Well, I hope you witnessed a good overview of the interaction of our researchers with different groups worldwide. I hope that you have a glance of the importance of this research. We have started with a very nice overview of the application of polymers in gas purification. And at the end, we were discussing the utilization of these gases and the importance of converting them into synthetic fuels. We had contributions from Dr. Martin Mittelbach as well on the oil-bearing materials being converted to SAF. We had catalysis work been represented here because without catalysis, nothing can be done efficiently. And I can only think that the overview given is a good example, a good showcase of the success of this CAPI Sprint project for us and for our research groups. I don't know if any one of you want to make use of the microphone now that we are closing the session. The microphone is open for any one of you who wants to use it.
Professor Ordonez and José Vargas from UFPR, Juan Ordonez from Florida State, would like to thank you for everything, Luis, and congratulate you on a very successful set of presentations. And let's hope to continue in that direction in the future.
Thank you very much, Vargas, for your contribution. Anybody else?
Yeah, also I'd like to thank Dr. Ramos for organizing this session. It's a very, very successful, also very, very impressive. I really enjoy this kind of the coupling the professor with student to share, the same presentation. That is wonderful. Also, I'm really happy to see Juliana, in this meeting. So hopefully we will continue our collaboration in the future. Thank you very much, everyone.
Most certainly so. Thank you, Tony, for your kind words. And well, I believe that in the benefit of time, it is more than past the moment of us to close the session. I thank you all again for your contributions. I really enjoyed the session, and I hope that this content, the session, the recording of the session, will be made widely available to all of you. I'm sorry for those who have tried to access the session through YouTube. Unfortunately, there were some technical problems that prevented them from following the session. Hopefully, this content will be available to them later on, and of course, they making them, let's say, available to enjoy the quality of the presentations we had so far. So thank you all again. Have a great lunch for those who are in Brazil. Have a great time for those who are in Europe and in the US or in Canada. Thanks again for all of you, and have a great time. See you next time somewhere.
Bye, guys. Bye, everybody.
Take care.
Bye. Thank you. Bye-bye, everyone.
Thank you. Bye, Martin.
Bye.
See you.
Bye-bye. See you
Take care.
See you.
in the future.
Bye.